Hello there, and welcome to Science for Sleep, where curiosity drifts quietly alongside calm, and science takes the long way around so that your thoughts can soften as you listen. Tonight, we're going to rest beneath the slow turning of the universe and follow a story that stretches farther than almost anything else we can imagine. It is a story about beginnings, about endings, and about what it means when even the most solid-seeming ideas of science are nudged, questioned, and sometimes left wobbling on their pedestals. Our guide tonight is not a person but a machine, one that has been set adrift in the cold emptiness of space to catch light so faint and so old that it began its journey before our planet had oceans, before our sun was born, before anything we know existed. That machine is the James Webb Space Telescope. Now, if you've heard about it already, you might know it as the big golden telescope with honeycomb mirrors that looks like something between a science fiction prop and an origami puzzle. But what it really is a time machine. Not the kind that whisks you into next week or back to when dinosaurs roamed, but one that patiently waits, with mirrors wide open, for photons, tiny packets of light, that have been travelling for billions of years. When those photons finally arrive, Webb gently cups them in its mirrors and shows us what the universe looked like when it was only a fraction of its current age. That sounds miraculous, but it's really just physics. Still, the feeling it gives us is closer to wonder than calculation. And here is where the story takes a twist. For more than half a century, the Big Bang Theory has been our anchor. The idea that everything, space, time, matter and energy, sprang from a hot, dense point about 13.8 billion years ago and has been expanding ever since. Entire careers, countless textbooks, and a mountain of cultural references lean on this picture. It's become so familiar that even people who don't think much about cosmology carry the phrase around as shorthand for the beginning of everything. But Webb, in its quiet, golden patience, has sent back pictures and data that don't sit comfortably within that story. They suggest galaxies that are far too large, far too bright, and far too mature to exist in the young universe, as the Big Bang narrative describes it. Imagine finding a full-grown oak tree inside a nursery of seedlings. That's the kind of jolt scientists felt. Before we go any further, I'd like to ask you something. Not about science, not about telescopes, but about you. Where are you listening from tonight? Is it evening where you are, the day winding down with the soft shuffle of familiar sounds? Or is it the middle of the night, quiet all around, your mind half anchored in wakefulness and half ready to float away? Maybe you're somewhere bright and bustling, listening to this as the world moves quickly around you. Wherever you are, whatever the clock says, you're here now, sharing this moment. That feels fitting, doesn't it? We're about to talk about time, distance, beginnings and endings. And yet right now, your experience of this story is anchored to the glow of a screen, a voice in your ears, and the slow turning of thoughts. If you find these kinds of journeys soothing, if they help you rest or spark gentle curiosity, I'd be ever so grateful if you clicked the like button, maybe subscribed, maybe even shared this with someone who could use a quiet moment too. It helps this little corner of calm find its way to more people, and it keeps these stories alive. But no rush. For now, just settle in. Let's ease into the vastness. When astronomers describe the James Webb Space Telescope, they often use words like ambitious or bold, but another word might be patient. It took decades of planning, billions of dollars, and the work of thousands of people scattered across the globe. Every single part had to fold, unfold, lock into place, and survive the long journey into space. When it launched on Christmas Day of 2021, the stakes were so high that many of the scientists involved admitted they barely breathed until the whole thing was safely in position 1 million miles away from Earth. The reason for all that precision is simple. Webb wasn't built to look at the familiar. Its job is to see things that are almost invisible, the faint stretched out light of galaxies that formed shortly after the universe began. To do that, It stares in infrared, a kind of light our eyes can't see, but which carries the fingerprints of the oldest stars and galaxies. And it worked. Almost immediately, Webb began sending back images so deep, so detailed, that even hardened astronomers, people used to numbers and charts, described them as breathtaking. In those first images, you can see galaxies not as a rare thing, but as countless swirls, dots and smudges stretching back as far as Webb's mirrors can reach. Every one of those points is a collection of hundreds of billions of stars. It's a staggering sight, like opening a door and realizing the room you thought was large is actually endless. But buried in those beautiful pictures was something stranger than beauty. You see, according to the Big Bang model, the early universe should have been chaotic, small, and slow to form structure. Galaxies should have taken hundreds of millions of years to settle, to grow heavy with stars, to gather into the elegant spirals and ellipticals we know today. But Webb found objects that seemed to skip the line, galaxies that looked far too developed, far too massive to belong to that early epoch. They shouldn't exist, and yet there they were, glowing across the abyss of time. It's like opening a baby photo album and finding a picture of a fully grown adult tucked between the infant snapshots. The timeline feels wrong, the story inconsistent, and yet the photo is real. That is what Webb has handed to us, evidence that our neat cosmic timeline may not be as neat as we thought. Now, before we chase that thread deeper, take a moment to notice how odd this is on a human scale. Most of us go about our lives with time neatly measured. Breakfast follows waking up. Work follows breakfast. Evening follows work. And we assume the universe has followed its own kind of order since its beginning. The Big Bang gave us that order. First the bang, then cooling, then stars, then galaxies. But Webb suggests that maybe the sequence wasn't quite so tidy. Maybe stars and galaxies appeared faster, brighter, more mysteriously than our equations had anticipated. That's not just a small error. It's a shift that touches the foundation of modern cosmology. And that's where the unease begins. Scientists love when data challenges ideas. It means new discoveries, new understanding. But they also know how fragile consensus can be. When a theory like the Big Bang has stood for decades, guiding entire fields of research, even a small crack in its certainty feels seismic. Webb has shown us galaxies like Sears 93316 and Glass Z13, whose light began travelling when the universe was supposedly just a few 100 million years old. Yet these galaxies look more like mature adults than cosmic infants. Their sheer size and brightness imply that stars formed and gathered in ways we don't yet understand. Some researchers have suggested that perhaps our estimates are off. Maybe the distances aren't quite what we think. Maybe the light is being magnified by gravitational lensing, the bending of light by massive objects. But even after careful checks, the data still suggests something unusual is happening. And so, slowly, carefully, cosmologists have begun to whisper the unthinkable. What if the Big Bang model, as we currently imagine it, isn't the full story? That doesn't mean the universe didn't expand from a hot, dense state. The evidence for that is still strong, from the cosmic microwave background to the observed redshift of galaxies. But maybe the details of how structure formed, of how quickly galaxies could assemble, of what conditions reigned in that early time are far stranger than we believed. Webb, in its quiet golden gaze, has simply forced us to admit how much we don't yet know. And that, in many ways, is what makes this story so human. For all our telescopes and theories, we're still a species staring up, guessing, revising, and sometimes being surprised. We may speak of the Big Bang with confidence, but a telescope 1 million miles away has reminded us that confidence is fragile, and the universe doesn't owe us consistency. Still, the questions raised by Webb's findings aren't discouraging. If anything, they're exhilarating. They suggest that the story of the universe is richer, stranger, and more surprising than our textbooks tell. They hint that there might be hidden processes, unknown physics, or even entirely new ways of understanding space and time waiting to be uncovered. And so, with that thought, let's keep moving deeper into the story, because if Webb has challenged the Big Bang, it has also challenged us to rethink what it means to say we understand the universe at all. It can feel strange to think of a telescope as a time machine, but that is exactly what the James Webb Space Telescope is. Unlike most tools we use in daily life, it doesn't simply look at what is happening right now. Instead, it gathers light that has been travelling across the universe for billions of years, light that left its source long before our species existed, sometimes even before our planet had fully formed. What Webb shows us is not the universe as it is in this instant, but the universe as it was long ago. Each photograph is less a snapshot and more a fossil, a relic carried by photons that have drifted through space since the earliest ages. To understand why this happens, it helps to slow down and think about light itself. When we turn on a lamp in a room, it feels as if the light appears everywhere instantly. But in truth, light has a speed. It is unimaginably fast compared to the speeds we know on Earth, but it is not infinite. It takes about 8 minutes for sunlight to reach Earth. That means every time you glance at the sun's golden light across the horizon, you're not seeing the sun as it is now, but as it was 8 minutes ago. If the sun were to suddenly vanish, the Earth would still bask in its glow for those 8 minutes before darkness fell. Extend that thought further, and you realize that the farther away something is, the older the light we see from it. The moon is just over a second away. The nearest star, Proxima Centauri, is 4 years away. Galaxies seen by Webb are billions of years away. That is why astronomers talk about look-back time. Observing something with Webb is not like turning on a live feed. It is more like looking into an archive, where the information is staggered across billions of years. Webb is designed specifically to reach into that deep archive, to stretch our vision farther back than any other instrument has managed before. The key is its sensitivity to infrared light, the kind of light that human eyes cannot detect, but which carries the signatures of very distant, very ancient objects. Because the universe has been expanding since its beginning, light from those early stars and galaxies has been stretched like elastic bands. What began as visible or ultraviolet light has been elongated into infrared by the time it reaches us. To catch it, we need a telescope that specializes in that wavelength, and that is what Webb is. The telescope itself is a marvel of engineering, but not in the sleek, shiny way we often picture futuristic machines. Its mirrors are hexagons of gold-coated beryllium, lightweight yet strong, carefully aligned to act as a single massive mirror over 6 meters across. This is what makes it so much more powerful than its predecessor, the Hubble Space Telescope. Where Hubble's mirror was about 2.5 meters, Webb's is more than twice the size, giving it the ability to gather far more light and reveal far fainter objects. And while Hubble worked mostly in visible and ultraviolet light, Webb was designed from the start to peer into the infrared. That single decision changes everything about what it can show us. To make those observations possible, Webb has to stay incredibly cold. Infrared light is essentially heat radiation. If the telescope itself were warm, its own heat would swamp the faint signals it is trying to detect. So engineers built an enormous sun shield, layered like a stack of silver sails to block light and heat from the Earth, the Moon and the Sun. Behind that shield, the telescope chills down to temperatures close to absolute zero, quiet enough to hear whispers of light that have been travelling for billions of years. It is almost eerie to think about, a golden eye peering into the dark hidden behind a vast parasol, listening to the faintest echoes of the cosmos. Because of that design, Webb does not orbit Earth like Hubble does. Instead, it sits at a place called the second Lagrange point, or L2, 1,000,000 miles away. There, the gravitational pulls of the Earth and Sun balance in such a way that Webb can remain in a stable orbit, always keeping its shield pointed toward the Sun and its mirrors toward the darkness of space. From that quiet perch, It scans the universe with remarkable steadiness. It does not blink. It does not rest. It simply gathers light, patiently, hour after hour, day after day. When the first images were released, the reaction was a mixture of awe and disbelief. There were the famous deep fields, showing galaxies upon galaxies, each one an island universe containing hundreds of billions of stars. Some were bright spirals, others faint smudges, some distorted by the bending of a light through gravity. Together they gave the impression of looking not at a handful of distant galaxies, but at a vast ocean with no end in sight. For the scientists who had worked on Webb for decades, those pictures were more than just pretty. They were proof that the telescope worked as planned, that the mirrors were aligned, the instruments functioning, and the universe opening itself in ways no one had ever seen before. But beyond that proof came something stranger. As astronomers studied those images more carefully, they began noticing galaxies that looked far too massive for their place in cosmic history. Remember, what Webb sees is the past. A galaxy observed at a redshift of 13, for example, is being seen as it was when the universe was less than 400 million years old. According to models, galaxies at that age should be small, irregular, just beginning to form their first generations of stars. But some of Webb's targets looked far more developed, with sizes and luminosities that rival galaxies billions of years older. That mismatch was what set off the first tremors of doubt about the neatness of the Big Bang timeline. Still, before diving too deeply into those controversies, it helps to pause and think about what it means to look at such ancient light. Imagine a beam of light leaving a star when the universe was only a few 100 million years old. It sets out on its journey, racing through expanding space. As eons pass, galaxies form, stars die, black holes awaken. Meanwhile, that photon just keeps going. It passes by countless structures, some of which might bend its path slightly through gravitational lensing, but still it presses onward. Finally, after more than 13 billion years, it encounters a mirror on a human-made telescope. That mirror redirects it, focuses it, and eventually a detector records its arrival. A photon's entire existence culminates in a tiny electronic signal on a telescope built by beings on a small planet orbiting an average star. It is almost overwhelming to realize that such a fragile chain of events can even happen. That fragility is part of why Webb is so carefully protected. Every observation is a long exposure, sometimes hours or even days of collecting photons from the same spot in the sky. Only by stacking those faint signals together can astronomers build a clear picture of the distant past. It is like letting rain collect in a barrel. One drop at a time is nothing, but over hours the water accumulates until you can drink from it. Webb's images are like that, barrels filled with drops of ancient light. The effect of seeing those images is not just scientific, but emotional. People describe them with words like humbling or spiritual. Even those who spend their careers studying cosmology admit that there is something unsettling about staring into such depth. You realize that your own life, your worries, your routines are specks on a timeline so vast that billions of years blur together. Webb is a scientific instrument, but it is also a mirror in another sense. It reflects our place back to us, reminding us how small we are, and yet how capable we are of reaching across time. Of course, the telescope is not just a camera. It also carries instruments that can split light into spectra, revealing what elements are present in distant galaxies, how fast they are moving, how old their stars are. Those spectra are like fingerprints, telling stories far richer than any image alone. With them, astronomers can reconstruct the chemical history of the universe, tracing how hydrogen and helium from the Big Bang gradually gave way to heavier elements forged in stars. In that way, Webb does not just show us where galaxies are, it shows us what they are made of, how they are evolving, and how they fit into the larger story of cosmic history. All of this makes the phrase, "the telescope that sees back in time," more than a catchy slogan. It is the literal truth. Webb's gift is to reveal moments in cosmic history that were previously beyond our reach. Where Hubble showed us galaxies as they were billions of years ago, Webb pushes even further to the very first stirrings of structure. It is a window into an era we have only speculated about until now. That window, however, has not just confirmed what we expected, it has unsettled it. And that is where the story turns from awe to curiosity, from celebration to questioning. Because if the universe looked different than predicted in those early times, what does that mean for the Big Bang model? It's important to remember that science is not a collection of unchanging truths but a process of revision. The Big Bang theory itself rose to prominence because it explained observations better than its rivals. Now Webb's discoveries may force revisions, refinements, or even entirely new frameworks. Some researchers argue that galaxies formed faster than we thought, meaning our models of star formation may need updating. Others propose that the distribution of dark matter in the early universe may have played a bigger role than anticipated. A few even suggest that the very assumptions about cosmic expansion need rethinking. Whatever the case, Webb has ensured that cosmology is once again a field in motion. It is worth keeping in mind that telescopes are not just passive observers, they are participants in the story of knowledge. Each new instrument changes the questions we ask, the answers we accept, and the way we see ourselves in the cosmos. Webb is the latest in that lineage, a telescope that sees not just space, but time itself, and by doing so it has reminded us that even the oldest stories about the universe can still surprise us. For most of the 20th century and well into the 21st, the Big Bang theory was more than just one idea among many. It was the backbone of modern cosmology, the framework into which nearly every other observation was fitted. The thought that it could be wrong or even incomplete in some crucial way felt almost unthinkable to many scientists. Not because they were unwilling to question it, science thrives on questioning, but because the Big Bang had earned its place through decades of evidence, predictions, and remarkable successes. It was not simply a story, it was a structure, one that organized our understanding of the universe from the grandest scales down to the smallest details. The origins of this idea go back farther than most people realize. In the early 1900s, Albert Einstein was reshaping physics with his theories of relativity, which included the startling realization that space and time were not separate but a single fabric called space-time. His equation suggested that this fabric was not static. It wanted to move, to stretch, or to collapse. At the time, however, the prevailing belief was that the universe was eternal and unchanging. To preserve that picture, Einstein added a cosmological constant to his equations, essentially a fudge factor to keep the universe balanced. He later called it his greatest blunder, but at the time it reflected how deeply the idea of a static cosmos was embedded in scientific and cultural thought. Then came observations that shook that view. Astronomers such as Vesto Melvin Slipher and Edwin Hubble measured the light from distant galaxies and found that it was shifted toward the red end of the spectrum. This redshift implied that those galaxies were moving away from us, and not just us, but from each other as well. The universe was expanding. Suddenly the static picture collapsed. If everything was expanding outward now, it must have been closer together in the past. Trace that logic back far enough, and you arrive at a beginning. A moment when the entire universe was compressed into an incredibly hot, dense state. That was the seed of the Big Bang idea. In 1927, a Belgian priest and physicist named Georges Lemaitre put these pieces together and proposed what he called the primeval atom, or cosmic egg, an initial explosion from which the universe unfolded. At first, the idea was controversial. Some scientists disliked its religious overtones, assuming that calling it a beginning smuggled theology into physics. Others simply thought the evidence wasn't yet strong enough. But as the decades passed, support grew. The discovery of the cosmic microwave background radiation in 1965 sealed it. Here was a faint afterglow bathing the entire sky, exactly what you would expect if the universe had once been a hot, dense fireball that expanded and cooled. The Big Bang went from hypothesis to widely accepted framework almost overnight. From then on, nearly every major cosmological observation fit within the Big Bang model. The abundance of light elements like hydrogen, helium, and lithium matched predictions from nucleosynthesis in the early minutes of the universe. The large-scale structure of galaxies, filaments, and clusters could be explained by the growth of tiny quantum fluctuations after the Big Bang. Even the acceleration of cosmic expansion, discovered in the 1990s, was folded into the theory with the introduction of dark energy. For scientists, this was a rare kind of triumph, a single framework that explained not just one or two features of the universe, but nearly all of them. That success gave the Big Bang theory a certain untouchable quality. When a theory explains so much, challenges to it are not easily entertained. It is not arrogance so much as practicality. If you are faced with a puzzle in cosmology, the natural first step is to see how it can be explained within the Big Bang framework, because odds are it can. Alternative models, like steady-state cosmology, which propose that new matter was constantly created as the universe expanded, keeping it eternal and unchanging in appearance, faded into obscurity because they failed to match the evidence as well. By the late 20th century, the Big Bang was not just the leading theory, it was the only serious contender. For the general public, the theory also took on a cultural life of its own. It appeared in textbooks, documentaries, and even sitcom titles. The phrase Big Bang became shorthand for the beginning of everything. People who had never opened a physics book still recognized the idea. Once there was nothing, then there was a bang, and now there is everything. That simplification is not quite accurate. The theory does not actually describe the moment of creation itself, but rather the evolution of the universe immediately afterward. But it shows how deeply the concept had taken root in our collective imagination. To question it felt like questioning gravity. Of course, within science, no theory is beyond scrutiny. Cosmologists continue to test and refine the Big Bang model, adding layers such as inflation, a rapid expansion in the earliest fraction of a second, to explain why the universe looks so uniform on large scales. They studied the tiny ripples in the cosmic microwave background to trace the seeds of galaxies. They built ever larger telescopes to probe deeper into the past. Each time the Big Bang framework held, its predictions matched observations with remarkable precision. So when the James Webb Space Telescope began sending back images that hinted at inconsistencies, the sense of shock was not because scientists had assumed the Big Bang was perfect. It was because the theory had proven so resilient for so long. To suddenly see galaxies that seemed to mature too quickly, to form too early, was like finding cracks in a wall that had stood firm for nearly a century. It didn't mean the whole wall would collapse, but it did mean the foundation might need re-examining. On a human level, this untouchability of the Big Bang speaks to how knowledge becomes trusted. At first, an idea is fragile. It competes with others, is doubted, and is tested. If it survives those tests, it gains strength. Over time, it becomes not just a hypothesis, but a framework, something that guides research and teaching. At that stage, questioning it becomes harder, not because people are unwilling, but because so much depends on it. Careers, institutions, and even personal identities become tied to the theory. To admit flaws feels destabilizing, yet science demands exactly that willingness to destabilize. That tension between trust in a framework and openness to challenge is where progress happens. It is worth noting that even as Webb's discoveries stir debates, few scientists suggest throwing out the Big Bang entirely. More often, they speak of revising it, extending it, or finding new physics that fills in the gaps. The analogy is less about tearing down a building and more about renovating one. Still, the fact that such renovation might be necessary is itself remarkable. For decades, the Big Bang felt untouchable. Webb has shown that no theory, however powerful, is immune to surprise, and perhaps that is the deeper lesson. The universe is under no obligation to conform to our expectations. We build models because they help us navigate, but they are only maps, not the territory itself. The Big Bang was, and still is, the best map we have, yet Webb reminds us that the territory is always richer, stranger, and more unpredictable than the lines we draw. With that reminder, we find ourselves moving naturally into the next question. If the Big Bang has been such a powerful and trusted framework, what exactly has Webb revealed that makes scientists hesitate, that makes them wonder if their untouchable foundation needs reinforcement? When the James Webb Space Telescope first opened its golden eyes and began transmitting data back to Earth, astronomers didn't just see pictures, they received whispers. Not literal sounds, of course, but signals so faint and so old that they felt more like echoes than images. Each pixel of light carried with it a story from a time when the universe was still young, when stars were just beginning to ignite and galaxies were first assembling. These faint glimmers are the whispers of the early universe, messages that took over 13 billion years to reach us. To imagine what these whispers are, think about the night sky you see with your own eyes. Even without a telescope, you're already looking back in time. The light from the Andromeda Galaxy, the nearest large galaxy to our own, began its journey about 2.5 million years ago. When you see its faint smudge with binoculars, you're witnessing it as it was long before humans walked the Earth. Now, stretch that idea farther. The galaxies Webb observes are not millions but billions of light years away. Their light began travelling when Earth didn't exist, when the Milky Way was only an idea waiting to form, when the universe itself was just out of infancy. That is what makes Webb's work so extraordinary. It doesn't just photograph far-off places. It listens to whispers from the deep past. The whispers come in the form of red-shifted light. Because the universe has been expanding since its earliest moments, any light travelling through it is stretched along with space itself. What might have left a star as blue or white arrives as a faint red glow, stretched all the way into the infrared. Webb is tuned to hear those stretched frequencies. It is like having ears designed for echoes that human ears cannot detect. When that light finally strikes Webb's instruments, it is translated into something we can interpret, turning faint whispers into visible portraits of galaxies, nebulae, and clusters. One of the first surprises hidden in those whispers was just how quickly structure appeared. The early universe, as imagined before Webb, should have been a simpler place, mostly dark matter and gas slowly clumping together. Stars would have been rare, galaxies even rarer. Yet the whispers told another story. They revealed bright, compact galaxies filled with stars that seemed far too old for their place in history. It was as if the universe had raced ahead of schedule, assembling grand structures in what was supposed to be its childhood. These whispers challenge more than just timelines. They also challenge our understanding of the physics that should govern those early times. According to established models, the first stars, sometimes called population 3 stars, should have been enormous, unstable, and short-lived. They would have formed out of pristine hydrogen and helium, blazing brightly before collapsing into black holes or exploding as supernovae. Their remnants would seed the universe with heavier elements, allowing later generations of stars to form more easily. But Webb's findings hint that galaxies in the early universe were already enriched with elements like oxygen and carbon, suggesting that star formation and death must have happened far faster than predicted. The whispers seem to say, "You thought you knew my pace, but I was swifter." There is also the matter of brightness. Some galaxies Webb has detected in the first few 100 million years after the Big Bang are astonishingly luminous. To shine that brightly requires either an implausible burst of star formation or something even stranger, such as the presence of unusually massive black holes feeding voraciously on surrounding matter. If true, that would imply that black holes too formed far earlier than expected. Instead of being the end products of long chains of cosmic events, they may have been participants in the very beginning, shaping galaxies rather than waiting to be shaped by them. For astronomers, interpreting these whispers is not easy. The data is complex, often ambiguous, and always subject to rechecking. Some scientists urge caution, noting that what appears to be an impossibly mature galaxy might in some cases be an illusion caused by lensing or misinterpretation of redshift. Others argue that even with such caution, the sheer number of surprising findings suggests something deeper is going on. The whispers are not isolated. They form a chorus that demands attention. The whispers also reach us in another form, the patterns in the cosmic microwave background. Though Webb does not study the microwave background directly, that task belongs to instruments like Planck and WMAP, the story it tells is linked. The microwave background is often called the afterglow of the Big Bang, the leftover heat from when the universe was only 380,000 years old. It is a whisper frozen in radiation, stretched thin across the entire sky. Combined with Webb's deeper whispers, we begin to hear a fuller song. The early universe was both more orderly and more chaotic than we imagined, stable enough to produce patterns in the microwave background, yet unruly enough to give birth to galaxies much earlier than our equations predicted. Hearing these whispers is not just a matter of science, but also of imagination. When you realise that photons from a galaxy at redshift 13 have been travelling longer than our solar system has existed, you can't help but feel a shiver. These photons passed by stars that lived and died before our planet was born. They crossed voids where nothing at all awaited them. They endured the expansion of space itself, stretched thinner and thinner, until finally, against all odds, they fell into Webb's mirrors. Each one is a survivor, a messenger carrying information across a gulf we can barely comprehend. To listen to such whispers is to be humbled, and yet, as humbling as they are, they also empower us. For the first time, we can piece together a record of cosmic dawn with actual data rather than speculation. We can test our models not against guesses but against real galaxies, real spectra, real light. The whispers are faint, but they are unmistakable. They are telling us that the universe may not be quite what we thought. This does not mean we must abandon the idea of the Big Bang. The overall picture of an expanding universe beginning in a hot, dense state still holds much of its power. But the details, the rate of star formation, the growth of galaxies, the role of black holes, the distribution of matter, are all being questioned by the voices arriving from those early times. In science, details matter, and sometimes it is in the details that revolutions begin. For the moment, astronomers are cautious. Each new dataset from Webb is pored over, debated, checked, and rechecked. There is excitement, yes, but also restraint. Whispers are easy to mishear. It takes patience to be sure that what you think you heard is truly what was said. But even with patience, the message so far is clear enough. The universe has more surprises to reveal. The whispers are not gentle confirmations of what we already knew. They are nudges, corrections, perhaps even challenges. They invite us to listen more carefully, to consider new possibilities, and to remember that science is always provisional. And so, as Webb continues to listen, and as we continue to interpret what it hears, we are reminded that knowledge is not static. What feels untouchable one day can be reshaped the next. The early universe is not silent. It is speaking faintly but persistently across billions of years, and we're just beginning to understand what it is saying. When astronomers first began examining Webb's earliest deep-field images, they expected to see faint smudges. The hope was to catch glimpses of galaxies so young and so primitive that they would barely resemble the great spirals and ellipticals we know today. Instead, what they found looked unsettlingly familiar. Some of those faint smudges were brighter than predicted, larger than expected, and in many cases already organised in ways that should have taken far longer to achieve. These were galaxies that, according to the timelines drawn by the Big Bang model, simply shouldn't exist yet. One of the first of these discoveries was a galaxy catalogued under the somewhat unglamorous name Glass Z13. The Z refers to its redshift, a measure of how much the light has been stretched by cosmic expansion. In this case, the redshift indicated that the galaxy's light began its journey only about 300 million years after the supposed Big Bang. That is staggeringly early. To put it in perspective, if the entire history of the universe were compressed into a single year, with the Big Bang at midnight on January 1st, and today, at the stroke of midnight on December the 31st, this galaxy would have appeared in the first few days of January. Yet despite its youth, it already contained enough stars to shine as a coherent galaxy. Another object, CEERS-93316, appeared to push the boundary even farther, perhaps as early as 235 million years after the beginning. Though subsequent analysis has introduced caution, even the possibility that such an object exists forces cosmologists to reconsider what is possible. Building a galaxy requires not only stars but time for gas to cool, collapse, ignite, and organize. To see such structures so early is like walking into a nursery and finding a teenager sitting among newborns. The puzzle deepens when we consider how massive some of these galaxies seem to be. Estimates suggest that they contain billions, even tens of billions of stars. That level of mass requires intense star formation in a very short period of time. According to older models, the early universe simply didn't have enough time to produce such giants. Stars were supposed to trickle into existence slowly, with galaxies growing gradually over hundreds of millions of years. Yet Webb shows us structures that look as though the universe skipped ahead in the script. This isn't just a matter of one or two unusual outliers. The early data from Webb suggests there may be a significant number of these unexpectedly mature galaxies. That abundance makes it difficult to dismiss them as statistical flukes or observational mistakes. Instead, it points towards something systemic. Either our understanding of galaxy formation is incomplete, or the broader framework of cosmology itself requires adjustment. One possibility is that star formation in the early universe was far more efficient than predicted. Perhaps clouds of gas collapsed faster, or the first stars were larger and burned brighter than anticipated, producing rapid enrichment of heavier elements. This would allow galaxies to mature quickly, explaining their brightness and apparent age. Another possibility is that dark matter, the unseen scaffolding that shapes galaxies, played a more decisive role early on, pulling matter together into structures with surprising speed. But even with such adjustments, the scale of the problem remains daunting. For some of these galaxies to exist, the processes of star formation and assembly would have to run at breakneck speeds, far faster than models comfortably allow. It would be like planting a seed and returning the next morning to find not just a sprout but a towering tree. Physics rarely works in such leaps. For some researchers, the discoveries hint at the possibility of new physics altogether. Perhaps our understanding of cosmic expansion, of how time and distance are related in those earliest moments, needs rethinking. Perhaps something about the nature of dark energy, or the behavior of matter under extreme conditions, is different from what we assume. These are speculative ideas, but the very fact that they are being entertained shows how unsettling Webb's data has been. What makes this even more striking is how solid the Big Bang framework has felt until now. For decades, astronomers have been able to predict what they should see at various epochs of the universe. Hubble, with its deep-field images, extended those predictions and largely confirmed them. Webb was supposed to continue the story, filling in earlier chapters, perhaps adding detail but not contradiction. Instead, it has handed us characters who seem to have wandered in from the wrong act of the play. Take, for example, the question of heavy elements. According to standard cosmology, the earlier stars formed from hydrogen and helium, the simplest elements left over from the Big Bang. Heavier elements like carbon, oxygen, and iron could only be produced in the hearts of stars and scattered into space when those stars died. This recycling process takes time. You would expect early galaxies to be poor in such elements. Yet some of the galaxies Webb has observed already show signs of enrichment. That means generations of stars must have lived and died within a few 100 million years, a rate of turnover far faster than our models suggest. Then there are the hints of supermassive black holes. Some of these early galaxies shine with a brightness that suggests not just stars but active galactic nuclei, the blazing disks of material falling into massive black holes. If true, that would imply that black holes weighing millions or even billions of times the mass of our Sun formed astonishingly quickly after the supposed beginning. How could such giants grow so fast in so little time? The question remains unanswered. To be clear, astronomers are cautious. Extraordinary claims require extraordinary evidence, and many of these early findings are still being checked and rechecked. Spectroscopic confirmations are needed to be absolutely sure of the distances and redshifts involved. Some galaxies may turn out to be closer than they appear, their apparent youth an artifact of unusual colours or lensing effects. But even with that caution, the number of suspiciously mature galaxies is too high to ignore. Something is being revealed in these images, even if its precise nature is still uncertain. For those listening from outside the world of astrophysics, the phrase "galaxies that shouldn't exist" might sound dramatic, almost sensational. But for scientists who have spent careers working with carefully tested models, it is a sober description of the tension between theory and observation. When theory predicts one thing and observation shows another, the theory must bend. That bending may be slight, a tweak to the rate of star formation, a new insight into dark matter, or it may be profound, a re-evaluation of cosmic history itself. For now, the galaxies stand as puzzles, their light insisting that our story of the universe is incomplete. They remind us that science is not about certainty, but about adjustment, about listening carefully to what the universe is telling us and reshaping our understanding accordingly. In that sense, these galaxies are less problems than opportunities. They are the universe's way of nudging us, saying, there is more to the story. Look again. As Webb continues to collect data, astronomers will no doubt find more of these anomalies. Each one adds weight to the growing sense that the early universe was busier, brighter, and stranger than we believed. And as those numbers grow, the questions will only deepen. What exactly allowed these galaxies to form so quickly? Was there something unusual about the physics of those first few 100 million years? Are we missing a key ingredient in our cosmic recipe? The galaxies that shouldn't exist are not just curiosities. They are clues. Clues that may eventually lead us to a more complete picture of the cosmos. But for now, they sit quietly in Webb's images, glowing across billions of years, asking us to reconsider what we thought we knew. When scientists first began to realise that some of the galaxies revealed by Webb looked older than they should, the term that surfaced again and again was maturity. That word carries weight because it doesn't just mean size. A mature galaxy is one that has gone through cycles of star birth and star death, one that has built a structure stable enough to shine brightly without falling apart, one that has gathered billions of stars into a coherent whole. In human terms, it's the difference between an infant just opening its eyes and an adult who has lived through decades of change. To see such maturity in the very early universe is puzzling in the extreme. Galaxies are not supposed to leap straight into adulthood. They are thought to begin as small, irregular clumps of gas and stars, slowly merging with others, gradually settling into the spirals and ellipticals we recognise today. This process takes billions of years. For comparison, the Milky Way itself took more than 10 billion years to reach its current size and shape. So when Webb shows us galaxies glowing brightly and looking massive only a few 100 million years after the beginning, the puzzle becomes obvious. How did they grow up so fast? The first piece of the puzzle lies in the rate of star formation. In the standard picture, the early universe was filled with hydrogen and helium gas. For stars to form, that gas had to cool, collapse under gravity, and ignite nuclear fusion. Cooling takes time, as does the accumulation of enough mass for large stars. Once the first stars formed, they seeded the universe with heavier elements. making subsequent generations easier to form. But this process is not instantaneous. It should take hundreds of millions of years before galaxies could shine with billions of stars. Yet Webb is showing us galaxies that already look full-bodied within that time frame. One explanation is that the first stars were far more massive than the average stars we see today. Massive stars burn hotter and live shorter lives, often just a few million years before exploding as supernovae. In that short span, they can produce and spread heavier elements rapidly, enriching their surroundings. If the early universe produced a large population of such stars, then perhaps enrichment happened far faster than expected, allowing galaxies to mature quickly. Still, this requires conditions that may stretch our current understanding of physics. Another possibility is that galaxies in the early universe formed through rapid mergers. If many small clumps of stars and gas collided and merged at an accelerated pace, they could assemble into larger galaxies sooner. The universe at that time was denser, with matter packed closer together, so collisions may indeed have been more frequent. But even with that advantage, the speed at which some of these galaxies seem to have grown still raises eyebrows. It would be like trying to explain how a city with skyscrapers and highways appeared only a few decades after the invention of the wheel. The timeline feels compressed. Then there is the question of structure. Maturity doesn't just mean mass, it means organization. Some of Webb's images show galaxies with hints of disk-like shapes, structures that should take long periods of gravitational settling to develop. For such order to exist so early suggests that the processes of galaxy evolution may be more efficient or more varied than our current models allow. Perhaps galaxies had pathways to stability that we have not yet imagined. This puzzle becomes even more complex when we add in the presence of black holes. Some of the brightest early galaxies may in fact be powered by supermassive black holes at their centres. If true, then black holes not only formed earlier than expected, but also grew at astonishing rates. Instead of being the slow products of stellar collapse and merger, they may have been seeded by processes we do not yet understand, such as direct collapse of massive gas clouds. If black holes were already in place at the dawn of galaxies, they could have accelerated the process of maturity by driving star formation and structuring their host galaxies. But again, this is speculative. The maturity puzzle also touches on the role of dark matter. In modern cosmology, dark matter is thought to provide the scaffolding upon which galaxies form. It does not emit or absorb light, but its gravity pulls ordinary matter into clumps, helping galaxies assemble. If dark matter behaved differently in the early universe than we think, if it clustered more quickly, for example, then galaxies could have formed faster. This would not overturn the Big Bang entirely, but it would require significant adjustments to our understanding of dark matter physics. To appreciate the scale of the puzzle, imagine trying to reconstruct human history by looking at photographs. You expect to see infants, toddlers, teenagers, and then adults in sequence. But instead you flip through the first pages and already see adults, fully grown, with lines on their faces and stories behind their eyes. You would begin to wonder if your timeline was wrong, if perhaps these adults came from somewhere else, or if human development is faster than you thought. That is the situation astronomers face now. The cosmic photo album is out of order, and the images defy our expectations. For some, this puzzle is exhilarating. It suggests that we're on the brink of new insights, perhaps even new physics. For others, it is unsettling, a reminder that decades of carefully built models may need serious revision. Both feelings are valid. Science thrives on excitement, but also requires humility. The puzzle of cosmic maturity is both a challenge and an invitation, asking us to expand our imagination while keeping our feet firmly on the ground of evidence. It is important to stress that no one is throwing out the Big Bang wholesale. The evidence for an expanding universe, for a hot, dense early state, remains strong. What is in question are the details of how quickly structure formed, how galaxies assembled, and what processes governed those early times. The puzzle is not whether the universe had a beginning, but how that beginning unfolded. And Webb, by listening to whispers of ancient light, has shown us that the unfolding may have been far more rapid and complex than we realised. As more data arrives, astronomers are racing to refine their models. Simulations are being run with new parameters, new assumptions about star formation, black hole growth, and dark matter behaviour. Some results suggest that the puzzle may be solvable within existing physics, if we allow for more extreme conditions in the early universe. Others hint that entirely new ideas may be needed. Either way, the process will take years, perhaps decades, to resolve. Webb has not closed the book on cosmology. It has opened new chapters, filled with questions waiting to be explored. For now, the puzzle remains. Galaxies that should not be mature are shining brightly, their light defying our timelines. They remind us that the universe is not obliged to follow our scripts, that nature often surprises us, and that the process of discovery is ongoing. If maturity appeared earlier than expected, then our sense of cosmic timing may need to be re-examined. The very way we measure and interpret the passage of cosmic history could be flawed. And so, as we move forward, we'll consider how light, distance, and expansion conspire to shape our view of time, and why waiting billions of years for a photon to arrive can make the universe feel both ancient and strangely immediate. One of the most difficult things to grasp about the universe is that everything we see is delayed. Nothing arrives at the moment it happens. Even here on Earth, light takes time to travel, though the distances are so small that we rarely notice. When you turn on a lamp, photons stream out and bounce around the room, reaching your eyes almost instantly. But even in that moment there is a delay. Light has a speed limit, 300,000 kilometers per second, unimaginably fast compared to anything in daily life, but still finite. That speed limit becomes obvious once distances stretch beyond our immediate surroundings. The light from the sun, for example, takes about 8 minutes to reach us. The sunlight falling on your skin left the surface of the sun while you were finishing a sentence or sipping from a glass. If the sun were to vanish right now, the sky would remain bright for those 8 minutes before reality caught up. The moon is just over a second away. Mars, depending on its orbit, can be between 3 and 20 minutes. Already, communication with spacecraft has to account for these lags. A command sent to a rover does not arrive instantly. It drifts across space, taking minutes to cross the gap. Now extend that thought outward to the stars. The nearest star system, Proxima Centauri, is more than 4 light-years away. The faint light we see from it tonight left that star around the time some of us were children, or before many of us were even born. Looking at it is like looking into a time capsule, a frozen message from years past. And as we move farther still, the delays grow larger, stretching from years to thousands of years, to millions and then billions. This is where the James Webb Space Telescope makes its mark. It is not looking at the nearby stars of our neighbourhood, or even the galaxies we might call close. It is aimed at the faintest, most distant points of light it can reach, galaxies so far away that their photons began travelling toward us more than 13 billion years ago. Imagine that. A photon leaves a newborn star when the universe itself is still in its infancy. It travels outward through expanding space, sometimes bent by the gravity of clusters, sometimes passing through nothingness for eons. Along the way, entire galaxies form and vanish, stars are born and die, planets coalesce and shatter, civilizations may rise and fall. Through all of this, the photon keeps moving. It never stops, never slows, just continues forward. And then, one day, after billions of years of uninterrupted journey, it happens to strike a mirror floating in space near a small blue planet. That mirror belongs to Webb. The photon is caught, measured, and transformed into part of an image we can see. Thinking about this is both humbling and disorienting. The night sky is not a snapshot of what exists now, but a layered record of the past. Some of the galaxies we see tonight may not exist anymore. Their light is still travelling, still arriving, but the galaxies themselves could have merged, faded, or been torn apart long ago. We live surrounded by ghosts illuminated by light that carries memories of things long gone. To realise this is to understand why astronomers call telescopes time machines. They do not show us the present universe, they show us the history of the universe. The concept of look-back time helps frame this. Each distance corresponds to an age. A galaxy 10 billion light-years away is being seen as it was 10 billion years ago. But here the puzzle deepens, because the universe itself is expanding. The space between galaxies stretches as the photon moves, so the actual distance now is even greater than the time the photon has been travelling. What we call a redshift is both a measure of distance and a marker of time. The higher the redshift, the farther back in history we are looking. Webb's specialty is reaching into the highest redshifts, the earliest chapters of cosmic history. This stretching of light means that the photons Webb receives are not in their original form. A photon that left a star in blue light may arrive stretched into infrared. That is why Webb was built to see in infrared. Without that capability, the earliest light would be invisible to us. It is not just distance that hides it. It is the expansion of the universe itself pulling the wavelengths longer and longer like taffy being stretched. Webb listens to those stretched out whispers and translates them back into signals we can study. It is staggering to think that every dot in Webb's images is the endpoint of a journey billions of years long. Not a single photon in those pictures is recent. They are all ancient travellers, emissaries from times we can barely imagine. To look at them is to witness history directly, without words, without interpretation, just raw light from the past. And yet, we cannot see them as they are now, only as they were. The present universe is hidden from us by the finite speed of a light. The farther we look, the older the story becomes. This has profound consequences for how we imagine the universe. We're not at the centre of a static sphere. We're at the centre of a time bubble. Everywhere we look, the deeper we gaze, the older the universe becomes. The cosmic microwave background, that faint glow detected by satellites, is the oldest light of all, dating back nearly 14 billion years. It is the edge of our visible history, the point beyond which light cannot reach us because the universe was opaque before that time. In a sense, we live inside a shell of light, with each layer corresponding to a different era. When astronomers talk about billions of years, the numbers can feel abstract, but try to ground it in something familiar. A human life might last 80 or 90 years. 10 lifetimes fit into a millennium. 100 millennia stretch back to before recorded history. 1 million years ago, our ancestors were just learning to control fire. 100 million years ago, dinosaurs still roamed the Earth. 1 billion years ago, the most complex life forms were simple colonies of cells. 13 billion years ago, the first galaxies were flickering into existence. That is the scale of time that Webb is peering into. Each observation reaches back across a gulf so vast that human history is a thin layer at the end of it, barely noticeable in the cosmic record. The sheer patience of light is part of what makes this so mesmerizing. A photon has no awareness, no destination, no purpose. It simply moves. And yet, by moving, it carries with it a record. The path it travels, the stretching of its wavelength, the interactions it endures, all of these preserve information about the universe through which it passed. By catching that photon, we become archivists of the cosmos, reading a message that was written long before our species existed. This patience creates strange paradoxes in our perception. If an astronomer says a galaxy is 10 billion light-years away, it is natural to imagine that we are looking at it as it exists 10 billion light-years from here. But in truth, what we see is not the galaxy now, but its ancient version. The real galaxy, if it still exists, has moved on, aged and changed. The picture we have is frozen in time. To compare it to the present is impossible. We are forever looking into the past, forever a step behind the true state of the cosmos. And yet this is not a limitation so much as a gift. Without the delay of light, we would have no history of the universe. We would see only the present, a single frame without context. With the delay, we can reconstruct the story. We can watch galaxies in their youth, trace their growth, and test our theories against the unfolding of time. The billions of years it takes light to arrive are not an obstacle but a window, one that allows us to glimpse eras long gone. The puzzle, of course, is that some of what we glimpse does not fit neatly into our models. Those mature galaxies we discussed earlier appear in snapshots taken just a few 100 million years after the supposed beginning. Their light took over 13 billion years to arrive, and yet what it shows seems ahead of schedule. The delay of light reveals not only history, but also the tensions in our understanding of that history. It is as though the universe is telling us, here is my record, now interpret it if you can. This is why telescopes like Webb are both thrilling and humbling. They give us unprecedented access to the past, but they also confront us with puzzles we cannot easily solve. Each photon is both an answer and a question. Each delay in light's arrival is both a gift of knowledge and a reminder of how much we still do not know. And so, when we gaze at Webb's images, we are not just admiring distant galaxies, we are witnessing the patience of light, the slow unfolding of cosmic history, and the mysteries hidden in that history. The billions of years it takes for light to arrive are the very reason we can have this conversation, the reason we can ask these questions, the reason we can even imagine the universe's story at all. When we look at the universe with instruments like the James Webb Space Telescope, what we are really doing is leafing through an old photo album, not one filled with pictures of ourselves or our families, but of the cosmos itself, stretching back to its very first moments. Each galaxy, each faint smudge of light in Webb's images, is a photograph from long ago, preserved in the form of photons that have finally reached us. Together, these images make up what could be called the baby photos of the universe. Of course, baby photos have a certain expectation built into them. When you look at an album of a child, you expect to see them small, fragile, just beginning to grow. Their features are soft, their movements unsteady, their world still limited. Later pictures show them developing, gaining strength, learning to walk, eventually becoming an adult. The order makes sense. Each stage follows naturally from the last. That is how human growth works. The same expectation has guided our understanding of the cosmos. We believed we would see galaxies first forming as faint, clumpy structures, simple and unrefined, gradually evolving into the grand spirals and giant ellipticals we see today. The baby photos were supposed to look like infants, but Webb's baby album has been surprising. Instead of faint, fragile galaxies just beginning to form, many of the earliest images reveal galaxies that already seem grown, filled with stars, organized, and sometimes enormous. It is as if you turned the page of a family album and found that in the first year, the baby already had the face of a teenager. The expected softness and fragility are missing. The record suggests maturity when the timeline says immaturity. That tension is what has sparked so much discussion among cosmologists. To understand why this is puzzling, it helps to look back at what we expected to see. In the earlier stages after the Big Bang, the universe was a hot soup of particles. As it expanded and cooled, atoms formed, and eventually the first stars ignited. These first stars, often imagined as massive, short-lived giants, should have dominated the scene, living fast and dying young, spreading heavier elements in their explosive deaths. Out of this cycle, galaxies were supposed to emerge slowly, built from many generations of star birth and death, merging into larger structures over time. The first baby photos of galaxies, then, should have shown small, irregular clumps of stars, messy beginnings, not polished adults. Instead, Webb's images show galaxies that already appear luminous and massive in the first few 100 million years. Some of them shine so brightly that they challenge even the most generous estimates of how quickly stars could have formed. This has forced astronomers to rethink their assumptions. Were the first stars even larger and brighter than we thought? Did galaxies form through rapid mergers at a pace far faster than predicted? Or is there something missing from our models entirely? The analogy of baby photos becomes even more striking when we compare Webb's observations to the cosmic microwave background. That faint afterglow of radiation, discovered in the 1960s, is often described as the universe's first portrait, its newborn picture, taken when it was just 380,000 years old. At that stage, the universe was still uniform, with only tiny fluctuations in density. Those fluctuations are what later grew into galaxies and clusters. The microwave background is like an ultrasound image, showing the infant before birth. By contrast, Webb's photos are like snapshots from the first year of life. The expectation was that these would show the earliest signs of development, simple forms beginning to take shape. Instead, they show complexity far beyond what should be possible in such a short time. One possibility is that we have misjudged how to read these baby photos. Maybe the galaxies we are seeing are not as massive as they appear. Perhaps their brightness is exaggerated by gravitational lensing, where light from a distant object is magnified by the gravity of an intervening cluster. Or perhaps the redshifts have been miscalculated, making the galaxies appear older than they are. Astronomers are working hard to confirm these details with spectroscopic data, which provides more precise measurements than images alone. But even with those checks, the overall picture remains surprising. The universe seems to have grown up fast. Another possibility is that the processes of galaxy formation were more efficient than we thought. If the first stars were truly enormous, they could have enriched their surroundings with heavy elements much more quickly, allowing later generations of stars to form with greater ease. This would accelerate the growth of galaxies, giving them the appearance of maturity even at a young cosmic age. If so, then the baby photos are not wrong, but our expectations of what a cosmic infant looks like may need revision. There is also the intriguing idea that black holes played a role. Some of the brightest early galaxies may harbour active black holes at their centres, consuming matter and shining with extraordinary luminosity. If black holes formed quickly in the early universe, perhaps through direct collapse of massive gas clouds, they could have shaped their host galaxies, driving rapid star formation and giving the impression of early maturity. In that case, the baby photos are showing us not just galaxies but partnerships between galaxies and black holes, developing together in ways we had not anticipated. What makes these photos so compelling is not only their scientific value, but also their emotional impact. When people look at images from Webb, they often describe a sense of awe, of seeing something almost beyond comprehension. The thought that we are looking at light that began its journey billions of years ago, showing us galaxies as they were in their infancy, is overwhelming. The fact that those galaxies already look grown adds another layer of mystery. It is as if the universe is winking at us through the photo album, saying, "You thought you understood my childhood, but there is more to the story." This tension between expectation and reality is at the heart of science. We make predictions, build models, and test them against data. Sometimes the data confirms what we expect. Other times it surprises us, forcing us to revise our ideas. Webb's baby photos are in the latter category. They are not just beautiful pictures, they are evidence that our understanding of cosmic growth is incomplete. They challenge us to think differently about how galaxies form, how quickly stars can emerge, and what roles dark matter and black holes play in the process. For now, astronomers are cautious in drawing conclusions. More observations are needed, more confirmations, more analysis. But the baby photos are clear enough to spark debate. They show that the universe in its earliest years was not as simple as we believed. It was active, dynamic, and perhaps even impatient, rushing ahead with galaxy formation at a pace that defies our timelines. As Webb continues its mission, more of these baby photos will arrive, each one adding detail to the cosmic album. With each new image, we will refine our understanding, adjusting our theories to match what the light tells us. It is a slow process, but one that mirrors the patience of the photons themselves, travelling for billions of years to bring us their message. When the first full sets of data arrived from Webb, the reaction among astronomers was a mix of excitement and hesitation. They had been preparing for this moment for decades, simulating what the telescope might reveal, predicting what the earliest galaxies should look like, and fine-tuning models of cosmic history. Everyone expected beauty. Everyone expected detail beyond what Hubble had ever delivered. But few expected to feel genuine disbelief. And yet, as they stared at those first processed images, many of them found themselves rubbing their eyes, not out of fatigue, but out of confusion. Part of that disbelief came from the sheer abundance of galaxies. The very first deep-field image released by Webb showed thousands of them, scattered like jewels across a patch of sky smaller than the size of a grain of sand held at arm's length. To astronomers, this was not just a pretty picture. It was an overwhelming reminder of scale. If such a tiny slice of sky contained so many galaxies, then the full sky must contain hundreds of billions, perhaps more. The universe was suddenly more crowded, more vibrant, more filled with light than many had dared to imagine. Even seasoned scientists described feeling dwarfed by the immensity of it. But the deeper disbelief came when they began analysing the light from specific galaxies. Some of them seemed far too massive, too luminous, too structured to exist at the redshifts implied by their colours. These were supposed to be the infants of the cosmos, barely learning to shine. Instead, they looked like galaxies in their prime. Astronomers compared notes, rechecked calculations, and in many cases assumed there must be mistakes. Perhaps the galaxies were closer than they appeared, their light distorted by intervening matter. Perhaps the instruments were miscalibrated. Perhaps they themselves were simply reading the data incorrectly. The thought that the universe might genuinely be misbehaving compared to the models was almost too much to accept at first. It didn't help that these results arrived so quickly. Webb had only just begun its mission. Normally revolutionary findings take years to emerge, trickling out after careful peer review and cautious analysis. Here, in the first months, the telescope was already shaking the foundations of cosmology. The speed of discovery was disorienting. Scientists who had dedicated their careers to refining the Big Bang framework suddenly found themselves facing evidence that threatened to undermine it. The sense of disbelief was not just about the data, but about how abruptly the ground beneath them seemed to shift. For many, the disbelief was coupled with excitement. This is, after all, what scientists secretly hope for: data that surprises, evidence that challenges, mysteries that refuse easy answers. A universe that behaves exactly as expected is scientifically satisfying but emotionally flat. A universe that misbehaves is frustrating, but it is also exhilarating. Still, excitement does not erase the shock. The galaxies Webb revealed felt like gate crashes at a carefully planned event, showing up too early, too polished, too confident. Astronomers rubbed their eyes because the scene did not match the script. One of the more dramatic reactions came in the form of hastily written papers. Within weeks of Webb's first images, preprint servers filled with studies analysing the unexpected galaxies. Some proposed explanations within existing physics, such as faster star formation rates or underestimated dust content. Others floated more radical ideas, suggesting new physics, modified cosmological parameters, or even alternatives to the Big Bang itself. The sheer volume of speculation reflected both the excitement and the disbelief. Scientists were scrambling to make sense of what they were seeing, trying to catch up to the universe itself. For those outside the field, the disbelief may seem strange. After all, hadn't the Big Bang theory been tested and confirmed for decades? Wasn't it supposed to be one of the most solid pillars of modern science? How could a handful of early galaxies shake that foundation? The answer lies in how science works. A theory can be strong, successful, and widely accepted, but it is never immune to new evidence. The Big Bang framework explains much: cosmic expansion, the microwave background, the abundance of elements, but it also makes predictions about how structure should form. If observations consistently violate those predictions, the theory must adapt. That adaptation may be small or large, but it is unavoidable. Astronomers rubbed their eyes in disbelief because the data seemed to suggest that the adjustments required might be larger than anyone had anticipated. The disbelief was not only intellectual but also personal. Many astronomers have spent their entire career studying galaxy formation, fine-tuning simulations, teaching students about the timeline of cosmic evolution. To be confronted with evidence that the timeline might be off is to feel a jolt at the core of one's professional identity. It is not that they are unwilling to change. Most welcome it, but change on this scale is disorienting. Like being told that a language you have spoken fluently for years suddenly has new grammar you must learn. It requires humility, patience, and a willingness to sit with discomfort. This is why the phrase paradigm shift is often used cautiously. True revolutions in science are rare. More often, theories are revised rather than discarded. The disbelief surrounding Webb's discoveries is not necessarily about the end of the Big Bang, but about the recognition that the neat, orderly picture we had of cosmic infancy may need a serious overhaul. That recognition is thrilling, but it also comes with a sense of vertigo. The map no longer matches the territory, and the journey forward will be less certain than before. Astronomers are not strangers to disbelief. The history of cosmology is full of moments when the universe refused to cooperate with expectations. The discovery that galaxies were receding from us was once shocking. The realization that the expansion is accelerating, driven by something we call dark energy, was met with skepticism at first. Each time, disbelief eventually gave way to new understanding. Webb's revelations may be the latest in this line of surprises, another reminder that the universe is not obliged to be simple. Still, the immediacy of the disbelief is hard to overstate. Scientists who attended early briefings described hushed rooms, furrowed brows, and moments of laughter that were more nervous than joyful. Some muttered that they would need to rewrite their lectures. Others admitted they weren't sure what to think. A few confessed to sleepless nights, their minds racing with possibilities. In the quiet corners of research departments, conversations ran late, fueled by both caffeine and curiosity. The universe had spoken, and its voice was not what they expected. As the months passed and more data arrived, the disbelief began to settle into something more productive. Hypotheses were refined, simulations adjusted, debates sharpened. The initial shock gave way to the slow, deliberate work of science. But that first moment, the moment of rubbing eyes in disbelief, remains a testament to how profoundly Webb has shifted the conversation. It is a reminder that no matter how confident we are in our theories, the universe always has the final word. And with that realization, the path forward becomes clear. If the galaxies Webb revealed seem too massive, too luminous, too mature, then the next step is to investigate them in detail, to analyze their light, measure their spectra, study their composition, and determine whether they truly are as old and large as they appear. The disbelief has already transformed into determination, and the puzzle has become a challenge. What exactly are these galaxies that defy our expectations? How can they shine so brightly, so early, in a universe that was supposed to take its time? As the first waves of Webb's data were poured over, the headlines often focused on a few specific galaxies because they seemed to embody the strangeness of what the telescope had uncovered. These were not faint smudges barely visible at the edge of detection. They were bright, surprisingly well defined, and in some cases staggeringly massive for their place in cosmic history. They have been called impossible giants, because according to our understanding of the timeline, they simply should not exist. One of the clearest examples is the galaxy nicknamed Glass-Zoo 13. When first analysed, its light appeared to have been emitted about 300 million years after the supposed Big Bang. That is incredibly close to the beginning, a time when most cosmologists believed galaxies should not yet have had the chance to form in any recognisable way. Yet there it was, glowing across billions of years, already massive enough to rival galaxies billions of years older. It wasn't alone. CEE RS-93316 and others catalogued with similarly technical names showed the same baffling qualities. They were large, bright, and rich in stars, more like fully grown cities than small villages. The puzzle of these giants lies in their sheer size. Building a galaxy is not quick work. Gas must cool, stars must ignite, generations of stars must live and die, enriching the environment with heavier elements that allow subsequent stars to form more easily. Clumps of stars must merge, gradually assembling into larger structures. To reach billions of stars in just a few 100 million years is like watching a sapling transform into a forest overnight. According to the rules we thought governed cosmic growth, there simply hasn't been enough time. Some have argued that the galaxies might not be as massive as they appear. Estimating mass from light is tricky. Brightness can be influenced by many factors: the rate of star formation, the presence of dust, even the activity of a central black hole. If these galaxies contain unusually bright, short-lived stars, they may look more massive than they really are. But even with such caveats, the numbers strain the limits of what models allow. To explain them, we must either accept an implausibly high rate of star formation, or consider that our understanding of the early universe is incomplete. The giants also challenge our sense of order because of their structure. Some of them appear to have disk-like features, hints of organisation that should take far longer to develop. In theory, galaxies begin as chaotic, irregular blobs. Over billions of years, gravitational interactions settle them into spirals or ellipticals. Yet here we see galaxies in the first few 100 million years already showing signs of order. That order adds to the sense of impossibility. It's not just their size that is startling, but the speed with which they seem to have matured. Black holes complicate the mystery further. Some of these galaxies are so luminous that the brightness may not be due solely to stars but to active galactic nuclei. Supermassive black holes consuming matter at a furious rate. If so, then black holes weighing millions or billions of times the mass of the Sun must have formed astonishingly early. But how? The standard picture is that black holes grow gradually, from the collapse of massive stars merging over time to become larger. To reach supermassive size in just a few 100 million years would require either a new mechanism of growth or the direct collapse of enormous gas clouds, bypassing the normal stages entirely. The giants hint that the universe may have taken shortcuts we do not yet understand. Some astronomers have floated the idea that perhaps our measurements of redshift are off. Redshift is the stretching of light due to cosmic expansion, and it is our primary tool for gauging how far away, and therefore how old, a galaxy is. But Webb's instruments are precise, and multiple measurements have confirmed that many of these galaxies truly do come from the early universe. The margins for error are not large enough to erase the problem. The giants remain, standing stubbornly in defiance of expectations. What makes them so fascinating is not just that they exist, but that they may be more common than anticipated. If they were isolated curiosities, we could dismiss them as oddities, rare exceptions to the rule. But Webb's deep field suggests that they are numerous, scattered throughout the early universe in greater numbers than models predict. This abundance makes it harder to explain them away. If giants keep appearing where only infants were expected, then the problem lies not with the galaxies but with our assumptions. To appreciate the scale of the issue, imagine predicting how many tall buildings you would find in a small town that was founded yesterday. You might expect a few huts or shacks, nothing more. Instead, you arrive to find skyscrapers, office towers, and bustling streets. One building might be an anomaly. A whole skyline demands an explanation. That is what Webb has handed us. A skyline in the early universe where only scattered lights were supposed to exist. Some researchers suggest that the solution may lie in unknown physics. Perhaps the properties of a dark matter allowed galaxies to assemble faster. Or perhaps the rules governing star formation under extreme conditions are different from what we see in the present universe. Others speculate more boldly, wondering if the expansion history of the cosmos itself might need revision. Could it be that the universe is older than we think? Could the rate of expansion have varied in ways not accounted for in our models? These questions hover at the edges of discussion, tantalizing but risky. Scientists are cautious, aware that extraordinary claims require extraordinary evidence, and yet, the giants remain, their light an undeniable fact. Theories must bend to match them, not the other way around. Already, computer simulations are being adjusted to test scenarios where star formation is more efficient, where black holes grow more quickly, where galaxies merge at astonishing rates. Some of these simulations can reproduce the giants, but only by pushing assumptions to their limits. It feels less like solving a puzzle, and more like patching a hole in a dam. The water will keep pushing until a stronger framework is found. For those outside the field, it might seem strange that a few galaxies could cause so much consternation. But in cosmology, details matter. The existence of impossible giants is not just about adjusting a number here or there. It is about the integrity of the story we tell about the universe. If the universe can produce such massive structures so early, then our understanding of cosmic history must be incomplete. And if it is incomplete, then there may be fundamental truths we have not yet discovered. That possibility is both unsettling and exhilarating. There is also a philosophical dimension to this mystery. When we say that galaxies should not exist, what we really mean is that they should not exist according to our models. The universe itself is under no obligation to conform to our expectations. These giants are not mistakes. They are realities. The mistake, if there is one, lies in our understanding. In this sense, the impossible giants are not problems to be explained away, but teachers, forcing us to reconsider what we thought we knew. As Webb continues its mission, we will no doubt find more of them. Each one will sharpen the questions, refine the models, and deepen the mystery. Already, astronomers are preparing follow-up observations using Webb's instruments to study the spectra of these galaxies in detail. The chemical fingerprints will reveal their compositions, star formation histories, and perhaps clues about the processes that built them. It will take time, patience, and debate. But the giants are not going away. They will continue to stare back at us, luminous and enigmatic, until we learn to understand them. If galaxies can defy expectations, what about the invisible frameworks that hold them together? What about the dark matter and dark energy that shape the universe at the larger scales? When scientists talk about the mysteries of the cosmos, two phrases often come up again and again: dark matter and dark energy. These terms sound dramatic, almost ominous, but they are really placeholders for ignorance. They represent the things we do not yet understand but cannot ignore. Together, dark matter and dark energy make up most of the universe, yet neither has ever been directly observed. We know them only by their effects, by the way they bend light, move galaxies, and accelerate cosmic expansion. If the impossible giants revealed by Webb are puzzling, it may be because they are whispering something to us about these unseen forces. Dark matter first entered the conversation nearly a century ago. In the 1930s, an astronomer named Fritz Zwicky noticed something strange while studying clusters of galaxies. The galaxies were moving too quickly to be held together by the visible matter alone. By all rights, they should have flown apart. To explain their cohesion, Zwicky proposed the existence of unseen matter, something that provided gravitational pull without emitting light. He called it dunkel Materie, or dark matter. At first, the idea was met with skepticism, but over the decades, more and more evidence piled up. The rotation curves of galaxies, the bending of light by gravitational lensing, the patterns in the cosmic microwave background, all pointed to the same conclusion. There must be more mass than we can see. Today, dark matter is thought to make up about 27% of the universe, compared to just 5% for ordinary matter, the kind that makes up stars, planets, and people. Yet we still do not know what it is. It could be exotic particles, weakly interacting with the normal matter. It could be something stranger still, a new aspect of physics we have not yet imagined. For now, it remains invisible, detectable only through its gravitational influence. Dark energy is even more mysterious. In the late 1990s, two teams of astronomers studying distant supernovae discovered that the expansion of the universe is not slowing down, as once assumed, but accelerating. Galaxies are not just drifting apart, they are racing away faster and faster. To explain this, scientists invoked a repulsive force permeating space itself, dubbed dark energy. It makes up about 68% of the universe, yet we know almost nothing about it. Is it a property of space itself, as Einstein once imagined with his cosmological constant? Is it something dynamic, a field that changes over time? The truth remains hidden. Together, dark matter and dark energy dominate the cosmos. The ordinary matter that makes up everything familiar is just a small fraction. This realization alone is enough to shake our sense of certainty. We live in a universe where the vast majority of what exists is unknown. The very words dark matter and dark energy are reminders that we are grasping at shadows, naming mysteries without truly understanding them. Now, when Webb shows us galaxies that seem too massive, too bright, too early, one natural place to look for answers is in these unseen realms. Perhaps dark matter behaved differently in the early universe than we thought. If it clumped more quickly, it could have accelerated galaxy formation, creating scaffolds for stars to gather upon far sooner than expected. Alternatively, maybe dark energy played a role, altering the rate of expansion in subtle ways that shifted the timeline of cosmic evolution. Either way, the giants might be signposts, pointing us toward new insights about these dark forces. There is a kind of irony in this. We built Webb to study light, the faintest, oldest light in the cosmos. Yet the questions it raises may lead us deeper into the dark. By revealing galaxies that should not exist, it is forcing us to confront the limits of our models that rest heavily on assumptions about dark matter and dark energy. If those assumptions are wrong, then the entire structure of modern cosmology may need revision. This uncertainty is not a flaw of science, but its strength. To admit uncertainty is to stay open to discovery. When astronomers first proposed dark matter and dark energy, they were not claiming to have solved mysteries, but to have named them. The names themselves are admissions of ignorance. Now Webb adds to that humility, reminding us that our ignorance may be greater than we thought. The giants, the rapid star formation, the unexpected maturity, all may be evidence that our picture of the dark is incomplete. It is worth pausing here to reflect on what it means to live in such a universe. Most of what exists is invisible, undetectable by our senses, accessible only through indirect clues. We move through a cosmos built on foundations we cannot see. The certainty we feel when we look at the stars is balanced by the uncertainty beneath them. This balance is part of what makes science a human endeavour. We seek clarity, but we also accept mystery. We name what we do not understand, not to diminish it, but to acknowledge it. For the scientist analysing Webb's data, this uncertainty is both frustrating and exhilarating. It means long hours of reworking models, running simulations, testing new hypotheses. It also means the possibility of breakthroughs, of uncovering truths that will change how we understand the cosmos. To wrestle with dark matter and dark energy is to wrestle with the very structure of reality, and the impossible giants may be giving us the clues we need to make progress. There are also more radical possibilities. Some theorists have suggested that perhaps we don't need dark matter and dark energy at all, that what we really need is a new understanding of gravity. Modified gravity theories propose that the equations of general relativity, so successful on many scales, might not hold on cosmic scales. If gravity behaves differently across billions of light years, then the anomalies we attribute to dark matter and dark energy might instead be signs of deeper laws we have not yet uncovered. Webb's discoveries could revive interest in these alternatives, pushing us to test whether the foundations of physics themselves need adjustment. But even if we stick with the standard model, the uncertainties remain profound. We do not know what dark matter is made of. We do not know why dark energy exists. We do not know why galaxies grew so quickly in the early universe. Each of these questions is daunting on its own. Together they form a web of uncertainty that stretches across cosmology. Webb has not solved these puzzles. It has deepened them, made them sharper, more urgent, more pressing. And yet, there is something comforting in this as well. The mysteries remind us that discovery is ongoing, that knowledge is not static but evolving. We live in a time when new instruments can overturn decades of assumptions in a single image. That is not cause for despair. It is cause for wonder. The darkness is not empty. It is full of secrets waiting to be uncovered. If galaxies appear too mature, if dark matter and dark energy complicate our understanding, then perhaps the real puzzle is time. The cosmic clock we have been using may need adjustment. The sequence of events we thought was orderly may be more complicated than we imagined. And so the next question becomes, how do we make sense of cosmic timelines when the evidence refuses to fit neatly within them? For more than a century, the idea of an expanding universe has been central to cosmology. It began with those first observations of galaxies moving away from us, their light stretched into the red part of the spectrum, and it has been reinforced ever since. The expansion explains why the night sky is dark rather than filled with endless starlight. It explains the cosmic microwave background as the cooled remnant of a once hotter state. It explains the apparent age of stars, the distribution of galaxies, and the large-scale structure of the cosmos. In many ways, it is the thread that ties everything together. But when Webb began sending back data that didn't fit, the unspoken question began to stir. Is expansion the whole story? Or is there something else we're missing? The expanding universe is not just a phrase, but a framework built on Einstein's general relativity. In those equations, space itself is dynamic, capable of stretching, curving, and evolving. The discovery that galaxies were receding from us was not a surprise once those equations were taken seriously. If space is elastic, then the universe can grow. That growth, traced backward, leads to the idea of a beginning in a hot, dense state. It is elegant, consistent, and supported by decades of observation. But elegance does not guarantee completeness. The galaxies that Webb has revealed in the early universe challenge the neatness of this picture. If expansion alone governed cosmic history, then structures should have emerged more slowly. Time should have been needed to form stars, to build galaxies, to organize matter into the shapes we see. Instead, we find what looks like maturity too early, brightness too soon, giants where infants should be. If expansion is not the full explanation, then what else could be at play? One possibility is that we misunderstand the rate of expansion itself. The Hubble constant, the number that measures how fast the universe expands, has been a source of tension for years. Measurements using nearby galaxies and supernovae yield a value that doesn't quite match measurements based on the cosmic microwave background. This Hubble tension has been one of the most persistent puzzles in cosmology. Now, with Webb's galaxies hinting at accelerated growth in the early universe, the tension feels sharper. Perhaps the expansion has not been uniform. Perhaps it varied in ways we don't yet grasp, speeding or slowing at key moments. Another possibility is that expansion is not the whole story, but part of a larger process. Some theorists have proposed that the universe may go through cycles, expansion followed by contraction, a kind of cosmic heartbeat. Others suggest that what we see as expansion might be a side effect of deeper, physical laws, ones we have not yet uncovered. In these scenarios, Webb's galaxies could be windows into processes that go beyond the simple picture of space stretching outward. There is also the question of whether the redshift we see, the stretching of light, is always due to expansion. Redshift has been our primary tool for measuring distance and time, but what if there are other effects that mimic it? Alternative ideas have been floated over the years, though none have gained the traction of expansion. Still, the unusual galaxies Webb has shown us keep the door cracked open for possibilities that once seemed fringe. For astronomers, the idea that expansion might not be the full story is both unsettling and intriguing. On one hand, the expanding universe has explained so much, from the afterglow of the Big Bang to the distribution of galaxies. To question it feels risky, like pulling at the thread that holds a sweater together. On the other hand, science advances when we tug at threads, when we ask whether the patterns we see are truly as neat as they appear. Webb's discoveries invite us to do just that. It is important to note that questioning expansion does not mean abandoning it. The evidence for expansion is overwhelming. Galaxies are receding, light is stretched, the microwave background is real. The question is whether expansion alone explains everything, or whether it is only part of a more complex tapestry. The giants and the rapid star formation may be signals that something else is woven into the fabric of the cosmos. This something else could be subtle. It might be variations in the density of dark matter, creating local pockets where galaxies could form more quickly. It might be the influence of dark energy behaving differently in the past than it does today, or it might be a new ingredient altogether, something we have not yet named. Whatever it is, Webb has reminded us that we cannot take the simplest story for granted. For many scientists, the expanding universe was once the untouchable foundation, the steady ground beneath their feet. Now it feels less like solid ground and more like an evolving landscape, still stable in many ways but with cracks appearing in unexpected places. Those cracks do not destroy the landscape, they reveal depth, layers, and complexity we had not seen before. The disbelief, the puzzles, the impossible giants, all are signals that expansion may be only part of the truth. There is also a human side to this uncertainty. People crave narratives with clear beginnings and endings. The Big Bang, followed by expansion, gave us such a narrative. It was simple, elegant, and complete enough to be shared not just in classrooms but in popular culture. To complicate that narrative is to step into messier territory. It means admitting that we may not know how the universe truly began, or what its ultimate fate will be. That kind of uncertainty is uncomfortable, but it is also honest. As Webb continues to gather light, we will learn more about whether expansion alone can account for what we see. Detailed spectra, careful redshift measurements, and larger surveys will help confirm or refute the existence of impossible giants. Already, teams are working to test whether the apparent maturity of these galaxies is real or an artifact. But whatever the outcome, the fact remains that the expanding universe is not beyond question. It is resilient, yes, but not untouchable. The mystery is not just scientific, but philosophical. What does it mean if expansion is only part of the story? What if the cosmos is more complex than even our most elegant theories suggest? These are the kinds of questions that keep scientists awake at night and that lull listeners into thought when whispered gently, as we're doing now. They remind us that science is not about final answers, but about ongoing curiosity, about listening to what the universe is saying, even when it surprises us. When scientists talk about the early universe, they often rely on timelines. Numbers appear in textbooks and lectures. A few 100,000 years after the beginning, atoms form. A few 100 million years later, the first stars ignite. Galaxies slowly follow, building their structures over the next billion years. These milestones give us a sense of order, a way to chart events across cosmic history. But the discoveries from Webb are showing us that these neat numbers may not be telling the full story. The timelines may be off, or incomplete, or based on assumptions that the universe itself has already overturned. The trouble with cosmic timelines begins with how we construct them. We cannot watch the universe in real time. We only see it through light that has taken billions of years to arrive. Each photon is a message from the past, but piecing those messages into a coherent history requires interpretation. We rely on models to connect the dots, to fill the gaps between what we can observe and what we infer. Those models are based on physics as we understand it. Gravity shaping matter, nuclear fusion powering stars, dark matter pulling structures together, dark energy driving expansion. When the observations line up with the models, the timeline feels solid. When they don't, the whole framework begins to wobble. Webb's images of unexpectedly mature galaxies bring this wobble into sharp relief. If galaxies billions of stars strong already existed within a few 100 million years, then our sense of how quickly events unfolded must be wrong. Either the processes of star formation were far faster than expected, or the timeline itself is mismeasured. Perhaps both. In either case, the neat picture of infancy followed by childhood, followed by adolescence is disrupted. The universe may have raced ahead of schedule, compressing billions of years of expected growth into a fraction of the time. Part of the difficulty comes from the way we measure time across cosmic scales. On Earth, we rely on the steady ticking of clocks, the cycles of days and years, the predictable rhythm of atomic vibrations. In the universe, the clock is expansion itself. Redshift tells us how much light has been stretched, which we translate into a measure of distance and time. But this translation depends on assumptions about how expansion has behaved. If those assumptions are even slightly wrong, our entire timeline shifts. A galaxy thought to be 300 million years after the Big Bang might in fact represent a different era altogether. The trouble with cosmic timelines is that they are only as good as the models behind them. There is also the human tendency to prefer neatness. We like to think of the universe as unfolding in clear stages, one event leading naturally to the next. But nature does not always move in orderly steps. Processes can overlap, accelerate, or diverge in ways that defy simple sequencing. The first stars may have ignited sooner than predicted, setting off a cascade of events that built galaxies rapidly. Black holes may have seeded structures early, altering the pace of growth. Dark matter may have clumped more efficiently, speeding up the assembly of halos. Each of these possibilities complicates the timeline, making it less like a neat chart and more like a tangled web. For cosmologists, this trouble is both frustrating and thrilling. On the one hand, decades of work have gone into refining the standard timeline. Simulations have been run, lectures written, textbooks published. To admit that the timeline may be wrong is unsettling. On the other hand, the very act of rethinking the timeline is what drives discovery. If Webb's data forces us to redraw the chart of cosmic history, then we are not losing knowledge but gaining it. The discomfort is the sign of progress. It's also important to remember that timelines are simplifications. They are attempts to compress vast complexity into manageable markers. When we say the first stars formed 200 million years after the Big Bang, what we really mean is that on average, across vast regions, enough stars had formed by that time to leave an observable trace. But the universe is not average. Some regions may have formed stars earlier, others later. Some galaxies may have matured quickly, others slowly. Webb's images may simply be showing us the extremes, the fast growers, the overachievers, rather than the averages. If so, then the trouble with the timeline is not that it is wrong, but that it is incomplete. Still, even extremes must be accounted for. If many galaxies are outliers, then perhaps they are not outliers at all, but evidence of a different underlying reality. The timelines we construct must stretch to include them, or else risk being misleading. This is the work now facing astronomers, to decide whether the Giant's Web has revealed rare exceptions or common features, and to adjust the cosmic clock accordingly. The trouble with cosmic timelines is not new. Throughout the history of cosmology, estimates of the universe's age have shifted as new data has arrived. In the early 20th century, some calculations suggested the universe was only a couple of billion years old, too young even for the Earth's rocks. Later refinements, based on better measurements and improved models, pushed the age to around 13.8 billion years. Each adjustment reflected better data, but also reminded us that cosmic time is not easy to measure. Webb may be the latest catalyst for another such adjustment. There is a more subtle aspect to this trouble as well. Time itself may not behave in the cosmos the way we imagine it on Earth. General relativity tells us that time can bend, stretch, and flow differently depending on gravity and motion. In the presence of massive objects, clocks run slower. Across expanding space, intervals stretch. When we speak of hundreds of millions of years, we're translating a cosmic experience of time into human terms, but the translation is never perfect. Perhaps part of our difficulty with the timeline comes from assuming that time is a universal, uniform backdrop, when in reality it may be more elastic and contextual than we appreciate. For listeners outside of science, this might sound abstract, but the essential point is simple. The timelines we assign to cosmic events are not fixed. They are interpretations, vulnerable to revision as new evidence arrives. Webb's discoveries are forcing such revisions now. Galaxies that should not yet exist according to the timeline are staring back at us, demanding to be included in the story. Their light does not lie. Our charts must bend to accommodate it. The philosophical weight of this is significant. Humans crave beginnings, middles, and ends. We like to imagine the universe as a narrative with a clear sequence. The trouble with cosmic timelines is that the universe may not conform to narrative structure. It may be messier, faster, slower, or more complex than we can easily tell. Webb's revelations are reminders that we are not the authors of the universe's story. We are readers, deciphering a book whose pages are billions of years old and written in a language we are still learning. If the timelines are troubled, if our cosmic clock is imprecise, what alternative stories might we consider? If the Big Bang is not the full account, what other beginnings have been proposed? When the Big Bang theory rose to prominence in the mid-20th century, it did so by offering a simple and elegant explanation that matched the evidence available at the time. The universe was expanding, so it must once have been smaller, hotter, and denser. The discovery of the cosmic microwave background made the case even stronger. It was a clean story. Everything began in a fiery birth nearly 14 billion years ago, and the cosmos has been cooling and expanding ever since. For many, this story became so familiar that it felt inevitable. But in science, no story is truly inevitable. There have always been alternatives, other ways of imagining the origin of the universe, and Webb's discoveries have given some of those stories a fresh relevance. One of the earliest rivals to the Big Bang was the steady-state theory. Proposed in the late 1940s by Fred Hoyle, Thomas Gold, and Hermann Bondi, it suggested that the universe had no beginning and no end. Instead of originating from a singular event, it was eternal, with new matter constantly being created to fill the gaps as the universe expanded. This kept the density of the cosmos roughly constant over time. The steady-state theory was appealing because it avoided the idea of a beginning, which many scientists and philosophers found uncomfortable. It also matched the observation of expansion. But when the cosmic microwave background was discovered, the steady-state model struggled to explain it. The afterglow of a hot, dense past was exactly what the Big Bang predicted, and exactly what the steady-state theory did not. Gradually, the steady-state idea faded from prominence. Yet the instinct behind it, that the universe may not have had a single dramatic birth, still lingers in alternative models. Another alternative is the idea of a cyclic universe. In this picture, the cosmos undergoes endless cycles of expansion and contraction. A Big Bang is followed by expansion, which eventually slows and reverses into a big crunch, collapsing everything back into a dense state. From that collapse emerges another bang, and the cycle begins anew. Versions of this idea have existed for centuries, even millennia, in both scientific speculation and philosophical traditions. In modern physics, cyclic models have been revived in various forms, sometimes involving branes and extra dimensions in string theory, sometimes involving quantum gravity effects that prevent singularities. The appeal of the cyclic idea is that it avoids the need for an absolute beginning. The universe is not a single story, but an endless series of stories, each one giving birth to the next. There are also models based on quantum mechanics that propose the universe emerged from fluctuations in a quantum vacuum. In these views, the universe is not created from nothing in the traditional sense, but from a seething field of energy where fluctuations can occasionally spark into full-fledged universes. Our cosmos would be just one bubble in a vast quantum froth, one fluctuation among countless others. This idea has gained traction in part because quantum mechanics is known to allow particles to pop in and out of existence briefly, borrowing energy from the vacuum. If such processes can create particles, why not entire universes? Closely related to this is the concept of the multiverse. According to some versions of inflationary theory, the rapid expansion that occurred in the earliest fraction of a second may not have happened just once, but may be an ongoing process in different regions of space. In this scenario, our observable universe is just one pocket of a much larger multiverse, each pocket with its own properties, perhaps even its own physical laws. This is a radical idea, difficult to test directly, but it has become a serious subject of discussion in cosmology. If true, then the Big Bang was not the beginning of everything, but only the beginning of our particular region. The larger multiverse may have existed long before, or may have no beginning at all. Some alternative stories are even more speculative. There are models in which time itself has no beginning, where what we call the Big Bang is merely a transition from one phase of the universe to another. There are scenarios where space and time emerge gradually from a deeper, more fundamental reality, such as a network of quantum information. In these pictures, the question of a beginning is reframed entirely. The universe as we know it is a layer of reality, not the whole of it, and what we think of as the start is just one step in a larger process. What makes these alternatives compelling in light of Webb's discoveries is that they allow room for complexity at the beginning. If the universe is older than we think, or if it did not begin in a single explosive moment, then the presence of mature galaxies early on is less surprising. In a cyclic model, for example, remnants of previous cycles could seed rapid galaxy formation in the next. In a multiverse scenario, conditions in our bubble may have favoured fast growth from the outset. Even in steady state-like ideas, galaxies may have had more time to develop than the traditional Big Bang timeline allows. Of course, each of these models comes with challenges. The steady-state theory cannot explain the microwave background. Cyclic models struggle to avoid entropy building up over cycles. Quantum fluctuation and multiverse ideas are often criticised for being untestable, at least with our current tools. But the value of these alternatives is not that they replace the Big Bang outright, but that they expand the space of possibility. They remind us that cosmology is not settled, that our dominant theory is strong but not invulnerable, and that we must be willing to consider other stories when evidence demands it. It is also worth noting that the Big Bang itself has evolved. The original version of the theory has been supplemented by inflation, dark matter and dark energy, each of which was added to explain observations the simpler model could not. In that sense, even the Big Bang has been an evolving story, incorporating new elements as needed. Webb's findings may simply be the latest push toward further evolution. Perhaps we will add new physics about star formation, or about dark matter behaviour, or about quantum effects in the early universe. Perhaps we will lean more heavily on alternative models, weaving them into the Big Bang rather than replacing it. Science rarely discards successful theories entirely. More often, it revises them, reshaping the narrative while keeping the parts that still hold true. For listeners, the key point is not which model will ultimately prevail, but that multiple models exist. The universe may have begun with a bang, or with a bounce, or with a fluctuation, or not at all in the sense we usually mean. The important thing is that we are humble enough to admit we do not know for sure. Webb has not given us final answers. It has given us puzzles that reopen old questions. And in doing so, it has reminded us that the story of the universe's beginning is not closed. The Big Bang is one of those ideas that has travelled far beyond the world of physics. It is not just a scientific model. It has become a cultural reference point, something that appears in classrooms, documentaries, books, and even comedy shows. People who have never read a paper on cosmology still know the phrase, and for many it represents the beginning of everything. Once there was nothing, then a bang, and now the universe exists. That is the simplified version, and it has a certain elegance to it. But the real scientific story has always been more complicated, and Webb's discoveries are pushing us to ask a difficult question. Did the Big Bang really happen the way we think it did? To answer that, we first have to clear up a common misunderstanding. The Big Bang was never meant to describe the actual moment of creation, the instant when the universe supposedly leapt into existence from nothing. What the theory really describes is the evolution of the cosmos from a hot, dense state. It begins fractions of a second after whatever that initial condition was, tracking the rapid expansion and cooling that followed. In that sense, the Big Bang has always been about what happened after the beginning, not the beginning itself. But over time, especially in popular culture, the idea blurred into a story of creation. The phrase Big Bang itself, coined somewhat dismissively by Fred Hoyle, helped reinforce the image of a single explosive birth. According to the Standard Model, the universe expanded from a state so hot and dense that atoms could not exist. As it cooled, protons and neutrons combined to form the first light elements: hydrogen, helium, and a trace of lithium. A few 100,000 years later, electrons joined nuclei to form neutral atoms, and light could finally travel freely. That released the cosmic microwave background, the afterglow we still detect today. Hundreds of millions of years after that, the first stars ignited, followed by galaxies, and the structure of the cosmos unfolded. This timeline has been tested repeatedly and has matched many observations. The abundance of light elements fits. The microwave background fits. The overall large-scale structure fits. On many fronts, the Big Bang has succeeded. But then comes the data from Webb. Galaxies appearing too early, too large, too mature. Stars enriched with heavy elements long before they should exist. Black holes that seem to have grown too massive too quickly. These findings don't necessarily overturn the Big Bang, but they complicate the picture. They force us to ask whether the universe's early history unfolded exactly as the model describes, or whether there were processes happening alongside it that we have not accounted for. One possibility is that the Big Bang happened, but the timeline afterward is different than we thought. Perhaps star formation began earlier, or ran more efficiently than our simulations predicted. Perhaps dark matter created scaffolds faster, allowing galaxies to grow quickly. If that is true, then the Big Bang still stands, but the details of its aftermath need serious revision. Another possibility is that our interpretation of the data itself is flawed. The galaxies Webb is seeing may not be as massive as they appear. Their brightness could be influenced by unusual populations of stars or by lensing effects that magnify them. If so, then the apparent contradiction may be less severe. But even then, the number of such galaxies is surprising, and the overall picture still suggests more activity in the early universe than expected. There are also more radical possibilities. Maybe the Big Bang was not the unique beginning we imagine, but a transition, one bounce in a larger cosmic cycle. Maybe what we see as the Big Bang was just our corner of a larger multiverse bubbling into existence. Maybe quantum fluctuations, string theory brains, or some deeper reality produced our observable cosmos in a way we don't yet understand. In such scenarios, the Big Bang as we describe it is real, but only as a local event, not the ultimate beginning of everything. Some critics of the Big Bang go further, suggesting that it may not have happened at all, at least not in the traditional sense. They point to alternative models where the universe has no beginning, where expansion is an illusion caused by changes in the laws of physics over time, or where what we think of as the birth of the universe is just one phase in a timeless reality. These ideas are speculative, and none yet have the explanatory power of the Big Bang. But Webb's findings have given them more attention, because they remind us that no theory is beyond question. It's important to stress that most astronomers are not abandoning the Big Bang. The evidence for it is too strong. The microwave background alone is difficult to explain without it. The abundance of elements, the large-scale structure, the observed expansion, all fit well within the Big Bang framework. What Webb has done is not destroy the theory but highlight its limits. It has shown us that the details of galaxy formation, black hole growth, and cosmic maturity may require new physics layered on top of the old. In that sense, the question is less, did the Big Bang happen? And more, did it happen the way we think it did? And the answer, increasingly, is probably not exactly. The broad strokes may be correct, but the fine details are open to revision. Science often works this way. A theory survives in general but evolves in specifics. Newtonian gravity was not wrong, but Einstein refined it. The Big Bang may be in the same position now, strong in outline but in need of correction in detail. For the public, this can be confusing. People like certainty, and the Big Bang has been presented for decades as a certainty. To now hear that it may not be the whole story feels like a reversal. But for scientists, this is natural. Theories are always provisional, always subject to change in the light of new evidence. Webb has simply delivered that new evidence faster and more dramatically than anyone expected. There is also something profound in the very act of questioning. Asking whether the Big Bang really happened that way is not an act of dismissal, but of respect. It means taking the data seriously, honouring the light that has travelled billions of years to reach us. It means refusing to bend the evidence to fit the theory, and instead bending the theory to fit the evidence. That is the heart of science. If the Big Bang did not unfold exactly as we thought, what else might the universe be hiding? What structures, what patterns, what echoes might reveal the deeper truth? When we think of the universe, it's easy to imagine it as a vast emptiness dotted with galaxies. That picture isn't wrong, but it is incomplete. The cosmos is not randomly scattered. It is arranged in patterns, immense structures that span hundreds of millions of light years. Galaxies gather not in isolation but along invisible highways of matter, forming a web-like structure across the universe. This is the cosmic web, the largest known structure in existence, and understanding it may be key to making sense of what Webb has been showing us. The cosmic web looks, in computer simulations, like a delicate lace of filaments, dense regions where filaments intersect host clusters of galaxies, while between them lie vast voids, regions of near emptiness stretching across unimaginable distances. The filaments themselves are made mostly of dark matter, unseen scaffolding that shapes the visible galaxies like beads strung on invisible strings. This web is not static. It formed from tiny fluctuations in the early universe, quantum ripples magnified by inflation and gravity, slowly pulling matter into strands over billions of years. What makes the cosmic web so fascinating is that it bridges scales. On one end, it is the architecture of the universe, setting the stage for where galaxies live and how they evolve. On the other, it is shaped by the smallest details of physics, from the behaviour of dark matter to the properties of the earliest light. It is both vast and subtle, a pattern so large that it only reveals itself when we look across billions of light years, yet so delicate that its threads depend on forces we cannot yet see directly. When Webb peers deep into space, it is not just catching sight of individual galaxies, it is glimpsing pieces of this larger tapestry. The distribution of those galaxies, their brightness, their clustering, all carry information about the underlying web. And here too surprises may be hiding. If galaxies formed earlier and more efficiently than expected, then the web itself may have developed differently. Its threads may have woven faster, its intersections may have gathered matter more quickly, its voids may have formed sooner. Webb may be showing us not only impossible galaxies but a cosmic web that matured ahead of schedule. The idea that the universe is connected in this way is both scientific and deeply human. We look for patterns, for connections, for structures that explain the chaos of experience. The cosmic web provides that structure on the grandest scale, but just as with galaxies, our understanding of it depends on models and simulations. We have mapped portions of it by studying the distribution of galaxies nearby, but the web at extreme distances in the early universe is harder to trace. Webb's observations give us new glimpses, but they also raise new questions. If the web formed faster, what does that say about dark matter? If its filaments are stronger or denser than predicted, what does that mean for our models of gravity? For scientists, one of the striking features of the cosmic web is its resemblance to other networks. The filaments look uncannily like neural pathways in the brain, or like the mycelium networks of fungi under forest soil. These analogies are not exact. Galaxies do not think, dark matter is not alive. But the similarity of form is intriguing. Nature seems to favour networks, from the microscopic to the cosmic. The cosmic web is the universe's way of connecting its parts, a structure that allows galaxies to grow, merge and evolve. If Webb is showing us that these connections formed earlier than expected, then it is not just galaxies that defy our timelines, but the web itself. Another layer of mystery lies in the voids. For all its filaments, the cosmic web is mostly empty space. Vast expanses exist where galaxies are rare or absent altogether. These voids are as much a part of the structure as the filaments, defined by absence rather than presence. They too may carry clues about the early universe. If voids formed differently than predicted, if they are larger or smaller, or distributed in unexpected ways, that may point to new physics. Webb's ability to see distant galaxies gives us new tools to measure these gaps, to map the emptiness as well as the fullness. The cosmic web also holds significance for the question of cosmic maturity. Galaxies grow not just by forming stars internally, but by drawing in gas along the filaments, streams of matter funneled into them by the web. If those filaments were more efficient in the early universe, then galaxies could have grown much faster. This could explain why Webb sees massive, mature systems so early. The giants may not have grown alone. They may have been nourished by the web itself, fed by its invisible threads, and yet the web is only partly understood. Dark matter remains hypothetical, inferred but unseen. The precise mechanisms of filament formation are still debated. The role of dark energy in shaping the web's evolution is even less clear. Webb's data may force us to revisit all of this. If galaxies appear where we did not expect them, then the filaments that connect them may also behave in ways that our models have not captured. The web may be stranger than we think, its threads more twisted, its structure more dynamic. For people outside of cosmology, the idea of the cosmic web carries a certain poetry, even though it is built on physics. It suggests that everything is connected, that galaxies are not isolated islands but parts of a larger fabric. When you look up at the night sky, you're not just seeing random points of light. You are seeing nodes in a web that spans the universe. Each star, each galaxy, is part of a pattern too vast for the naked eye to perceive, but revealed by science as one of the most beautiful structures in existence. In a way, Webb is doing for the cosmic web what it has done for galaxies, turning vague outlines into sharper pictures. But the sharper those pictures become, the more puzzles they reveal. If the web's threads were already in place earlier than expected, then the standard timeline of cosmic evolution must once again be adjusted. If the web's filaments carried matter faster, then our understanding of dark matter's role must be refined. The web does not just support galaxies, it challenges our theories, demanding that we account for its complexity. When we listen to the story of the universe, We're not only looking at images of galaxies, we're also listening for vibrations that have echoed across billions of years. These ripples are faint, buried in background radiation and large-scale structures, but they are among the most valuable clues we have about how the cosmos grew. Some of them have been studied for decades. Others are only now being revealed in detail, thanks to telescopes like Webb. Together they form a kind of hidden soundtrack to cosmic history. One of the most famous echoes is the cosmic microwave background. It is often called the afterglow of the Big Bang, a sea of radiation released when the universe was only a few 100,000 years old. Before that time, the cosmos was a hot, opaque plasma, where light could not travel freely. As it expanded and cooled, atoms formed, and suddenly light was released. That light has been travelling ever since, stretched by expansion into microwaves. We detect it today as a faint uniform glow across the sky, but on closer inspection, it is not perfectly uniform. Tiny fluctuations exist, differences in temperature only a few parts in 100,000. Those fluctuations are the fingerprints of early ripples in density, ripples that later grew into galaxies and clusters. These tiny variations are like the faint echoes of a drum beat struck in the earliest moments. They tell us about the conditions of the universe at its infancy, about how matter and radiation interacted, and about the seeds of structure that later formed the cosmic web. When satellites like COBE, WMAP, and Planck mapped the microwave background, they gave us some of the most precise measurements in cosmology. Those measurements confirmed many predictions of the Big Bang model, such as the overall geometry of the universe and the relative abundance of elements. For decades, they seemed to solidify the story. But Webb now adds a twist. By showing us galaxies that appear too early, it forces us to re-examine how those ripples evolved. The echoes match one part of the story, but the galaxies hint at something more complex. Another kind of ripple is seen in the large-scale clustering of galaxies. As sound waves travelled through the hot plasma of the early universe, they left imprints in the distribution of matter. These imprints are called baryon acoustic oscillations, and they can still be detected today in the way galaxies are spaced. They provide a kind of standard ruler for cosmology, a way to measure distances and test the expansion of the universe. Observations of these oscillations have been one of the key supports for the model of dark energy accelerating expansion. But if galaxies grew faster and earlier than expected, then the interpretation of these oscillations may need to be reconsidered. The ruler may still be there, but perhaps the marks on it are not as evenly spaced as we thought. There are also forgotten clues, signals that have long been noted but often set aside because they did not fit neatly into the prevailing model. For example, some quasars, those luminous beacons powered by supermassive black holes, seem to exist surprisingly early. Their brightness and size have always been difficult to explain within the standard timeline. Webb's discovery of giant galaxies only adds weight to those anomalies. Perhaps the quasars were not exceptions, but part of a larger pattern. Perhaps the clues were there all along, waiting for enough evidence to force us to pay attention. Another forgotten clue lies in the so-called Hubble tension. As I mentioned earlier, measurements of the expansion rate differ, depending on whether we look at the nearby universe or the distant past. This discrepancy has been known for years, but it has grown sharper as measurements have improved. Some have hoped that it might simply be an error in calibration. Others suspect it is a sign of new physics. Webb's galaxies may be pointing in the same direction, adding weight to the idea that our timeline is skewed. The clues are not isolated. They are part of a chorus, each one faint on its own, but together suggesting that the story is incomplete. Ripples also appear in the way light bends as it travels through space. Gravitational lensing, predicted by Einstein, causes the paths of photons to curve around massive objects. By studying these distortions, astronomers can map the distribution of dark matter and test the growth of structure. Already, lensing surveys have found hints of discrepancies, small mismatches between theory and observation. Webb, with its sharp vision, is contributing new data to this effort. Each distorted arc, each magnified galaxy, is another ripple, another clue about how matter is distributed and how quickly structures formed. What ties all of these ripples and echoes together is that they are indirect. They are not galaxies we can see with our eyes, but patterns we must interpret. They require careful analysis, sophisticated models, and a willingness to accept that the universe may not always cooperate with simplicity. They are like faint background music that only becomes audible if you listen closely. Webb has not replaced these earlier clues but has joined them, adding new harmonies and new dissonances. For scientists, the challenge is to weave these ripples into a coherent picture. The microwave background tells us one thing. Baryon oscillations tell us another. Lensing reveals yet another. And now, Webb's galaxies complicate the pattern further. The echoes agree in some ways, but diverge in others. The task is not to discard them, but to reconcile them, to find a story that makes sense of them all. For listeners outside the field, it may feel like science is contradicting itself. One clue says one thing, another says the opposite. But this is how progress happens. Each clue is a piece of a larger puzzle, and only when the pieces are all in place will the picture become clear. Disagreement is not failure. It is the sign that the puzzle is alive, that discovery is still happening. It is worth remembering, too, that many clues once forgotten have later turned out to be crucial. The expansion of the universe itself was once a surprising result, not easily accepted. The discovery of the microwave background was at first seen as noise in an antenna. Even dark energy began as a discrepancy in supernova measurements. Webb's findings may feel disruptive now, but in time they may become the foundation for a new understanding. The echoes we hear today may one day be recognized as the first notes of a larger symphony. And as we consider these ripples and echoes, the story naturally deepens into something more reflective. These signals are not just measurements. They are reminders of how fragile and provisional our knowledge is, how easily we can overlook a clue if it does not fit the story we prefer. They invite humility, the recognition that the universe is under no obligation to be simple. When astronomers gaze through telescopes, they are not only practicing science, they are also, whether they admit it or not, engaging in philosophy. To ask where the universe came from, why it looks the way it does, and whether it will last forever, is not just to measure photons and equations. It is to reach into the deepest questions humans have ever asked. The stars invite both calculation and contemplation. They demand precision, but they also stir wonder. Webb, with its golden mirrors and astonishing reach, has sharpened our calculations, but it has also reignited our wonder. The strange galaxies, the impossible giants, the ripples and echoes, these are not only puzzles for physics, they are philosophical provocations. At its heart, philosophy among the stars begins with humility. We live on a small planet orbiting an ordinary star in a galaxy that is just one among billions. For most of human history, this was unknown. The night sky looked like a dome, and Earth felt central. Now we know otherwise. And yet, even with all we've learned, Webb reminds us that our knowledge is fragile. We thought we knew how galaxies should form. We thought we understood the sequence of events after the Big Bang. But the light from the early universe suggests otherwise. This humility is not defeat. It is the starting point for wisdom. There's also a philosophical lesson in the very act of looking back in time. Every photon Webb collects is billions of years old. To see a galaxy is to see its past self, not its present reality. We never see the universe as it is, only as it was. In everyday life, we imagine that perception is immediate, but the stars remind us that perception is always delayed. Even here on Earth, light takes time to travel. The moon is a second away, the sun is 8 minutes, the nearest star is years. The cosmos magnifies this delay into billions of years. To live in the universe is to live in a constant dialogue with the past. That is not just a scientific fact, it is a philosophical reflection about time, memory, and the limits of our perception. Philosophy also emerges in the way we interpret uncertainty. Science thrives on doubt, on testing and revising, on never being fully satisfied. but as human beings we long for certainty. We want stories with clear beginnings and endings. The Big Bang provided such a story, a fiery start, an expanding cosmos, a long unfolding. Webb complicates that story. The timelines may be off, the details may be wrong, the beginning may not be what we thought. This uncertainty can feel unsettling, but philosophically, it can also be liberating. To admit we do not know is to remain open. It is to resist finality and embrace the possibility of new discovery. There is another dimension too, meaning. What does it mean that the universe is filled with billions of galaxies? What does it mean that most of what exists is dark, unseen, unknown? Science can describe the mechanics, but it cannot dictate the meaning. That is left to philosophy, to culture, to individuals. Some find insignificance in these scales, feeling dwarfed by the immensity. Others find significance precisely in the act of knowing, in the fact that creatures on a small planet can even ask these questions. Both responses are valid. Both are part of philosophy among the stars. The stars also invite us to reflect on beauty. Webb's images are not only scientific data, they're also aesthetic experiences. The colours, the shapes, the delicate arcs of light bent by gravity, they move people. For centuries, beauty has been linked to truth, the idea that nature's order is expressed in harmony and elegance. But beauty is also subjective, a response we bring to what we see. The fact that Webb's images move us so deeply suggests that science and art are not separate realms, but overlapping ways of engaging with reality. The universe is not only to be understood, it is also to be admired. There is an ethical side to this philosophy as well. To study the stars is to recognize our smallness, but it is also to recognize our responsibility. We live in a fragile corner of the cosmos, on a planet that sustains life, in a universe that seems largely indifferent to it. This recognition can sharpen our sense of care, for our world, for each other, for the conditions that allow us to gaze at the stars at all. Webb's discoveries are not just about distant galaxies. They are reminders of the preciousness of our own existence. The stars have always carried philosophical weight. Ancient cultures told stories about them, myths woven into constellations, lessons inscribed in the sky. Modern science has replaced myth with measurement, but the impulse is the same. We look up and wonder. We tell stories to make sense of what we see. Today, the story involves redshifts and dark matter rather than gods and spirits, but it is still a story, still an attempt to connect ourselves to the cosmos. Webb's contribution is to expand that story, to show us images that challenge our old narratives and force us to imagine new ones. And so, philosophy among the stars is not an alternative to science, but a companion to it. Science tells us what is, or at least what seems to be. Philosophy asks what it means, and how we live with it. Together they form a more complete response to the mysteries of the universe. If Webb is already challenging our understanding, what might future discoveries bring? What tools, what ideas, what philosophies will we need to make sense of them? When the James Webb Space Telescope was first imagined, the goals were ambitious but specific. It was designed to peer into the earliest moments of cosmic history, to see the first stars and galaxies forming, to study planets around distant stars' suns, and to refine our understanding of how the universe has unfolded. Engineers worked for decades, solving problem after problem, folding its golden mirrors into a launch-ready package and sending it 1 million miles from Earth to a quiet perch in space. The mission was a marvel of human ingenuity. But what Webb has truly given us goes far beyond its stated objectives. It has given us not just answers, but questions. Not just images, but perspectives. Not just data, but an entirely new sense of where we stand in the cosmos. The first gift Webb has given us is vision. Its infrared eyes pierce through dust and distance, revealing galaxies and stars invisible to any other telescope. It has allowed us to see the universe as it was billions of years ago, with clarity that Hubble could never achieve. The sheer beauty of its images is itself a kind of gift, a reminder that science is not only about measurement but also about awe. People who may never read an astrophysics paper can still feel the wonder of a Webb image, still sense the immensity of the universe in the arcs of light and the shimmering clusters. In this way, Webb has given us a shared experience of wonder, a common ground where science and humanity meet. The second gift is disruption. Webb has not simply confirmed what we expected. It has unsettled us, shown us galaxies too big, too bright, too soon. It has raised doubts about timelines we thought were secure and about models we thought were complete. For scientists, this disruption is priceless. It forces creativity, demands new theories, and ensures that cosmology remains a living, evolving field. Without disruption, science stagnates. With it, science thrives. Webb's unsettling discoveries are not failures. They are the very heartbeat of progress. Another gift is humility. In revealing galaxies that defy our expectations, Webb has reminded us that we are not masters of the universe's story. We are readers, interpreting fragments, trying to piece together a narrative from incomplete evidence. Every time we think we understand, the cosmos finds a way to surprise us. This humility is not discouraging. It is grounding. It reminds us that discovery is endless, that there will always be more to learn, more to explore, more to imagine. Webb has also given us connection. Its discoveries are not confined to the world of professional astronomers. They have been shared globally, reaching classrooms, news outlets, and living rooms. People who might never have thought about cosmology are now discussing galaxies 13 billion years old, debating the Big Bang, and wondering about the nature of time. In a world often divided, Webb has provided a moment of unity, a reminder that we all share the same sky, that we're all participants in the same cosmic story. On a deeper level, Webb has given us a confrontation with mystery. The mature galaxies, the impossible giants, the unexpected structures. These are not just scientific puzzles. They are reminders of the limits of human knowledge. To be confronted with mystery is to be reminded of what it means to be human, to ask, to seek, to wonder. Webb has placed us again at the edge of the known, asking us to lean into the unknown. It has also given us a renewed sense of history. The light Webb collects began its journey billions of years ago, long before our species existed, long before our planet formed. To capture that light now is to connect with a history that is not ours alone, but cosmic. Webb has expanded our sense of past, stretching it from the brief span of human memory to the near beginning of time itself. This expansion of perspective is as much a philosophical gift as a scientific one, and Webb has given us possibility. By raising questions about dark matter, dark energy, cosmic timelines, and the Big Bang itself, it has opened doors to new physics, new theories, new ideas. These possibilities may take decades to explore. Some may turn out to be wrong, others may revolutionize our understanding. But the fact that the possibilities exist is itself a gift. It means the future of cosmology is alive with potential. For the engineers and scientists who built Webb, the gift is also personal. To see the telescope succeed after so many years of doubt and delay is to witness the triumph of persistence. Webb was almost cancelled many times, its cost ballooned, its complexity seemed insurmountable, but it was finished, launched, and deployed perfectly. The fact that it works at all is a gift to the human spirit, a testament to what we can achieve when we refuse to give up. For humanity as a whole, the gift is perspective. To see galaxies forming so soon after the beginning, to witness light that has travelled for billions of years, is to be reminded of our place in the cosmos. We are small, but we are capable of great vision. We are temporary, but we can reach across time. Webb's images are not just data points. They are mirrors, reflecting back our own hunger to know, our own need to explore, our own unending curiosity. As we continue to analyse Webb's findings, more gifts will come. Some will be scientific, measurements of exoplanet atmospheres, refinements of cosmic expansion, details about star formation. Others will be intangible, inspiration for a new generation of scientists, wonder for millions of people, a sense of belonging to something larger. Webb's legacy will not just be in papers and data archives, it will be in the way it has expanded human imagination. And so, what Webb has really given us is not a single answer but a way of seeing. It has given us questions we did not know to ask, beauty we did not expect to see, and humility we did not know we needed. It has given us a reminder that the universe is stranger, richer, and more surprising than we imagined. As we arrive at this quiet moment together, it feels natural to look back on the journey we've taken through the stars, through light that has travelled across billions of years, through galaxies that should not exist, through ripples, echoes, and mysteries that stretch the imagination. The James Webb Space Telescope has not only changed what we know about the universe, it has changed how we feel about it, how we think about it, and how we place ourselves within it. What lingers most is the scale. A photon leaving a star more than 13 billion years ago, travelling unceasingly across expanding space, finally met a mirror suspended in the dark. That tiny interaction, the meeting of ancient light and human technology, has given us images that change everything. There is something profoundly moving about this. The universe has been telling its story all along, and only now, with instruments like Webb, are we learning to listen. The discoveries we've explored, the impossible giants, the galaxies too old for their place in the timeline, the strange web of filaments, the forgotten clues reawakened, all point to the same truth. The universe is not finished surprising us. We thought we had a stable framework, but the cosmos has revealed new complexity. This is not discouraging. It is exhilarating. It means there will always be more to learn, always more to uncover, always new puzzles waiting beyond the horizon of our current knowledge. In reflecting on all of this, one can't help but feel the tension between smallness and significance. We are small, yes. Our entire history is a blink compared to the billions of years Webb's light has travelled. Our planet is tiny, our lives brief, and yet we are the ones building telescopes, sending them into space, unfolding mirrors like golden petals, and catching photons that began their journey before Earth even existed. In that sense, we are deeply significant. The universe has given rise to beings capable of noticing it, capable of questioning it, capable of wondering about its beginnings and its fate. There is also beauty in the not knowing. Webb has unsettled us, shaken the neatness of the Big Bang story, and reminded us that certainty is always provisional. But uncertainty is not weakness. It is a kind of strength. It means we are still listening, still open, still ready to be surprised. To live with uncertainty is to live in curiosity, and that may be the most human quality of all. As you think about these things, about galaxies born before their time, about light that has travelled longer than any measure of history we can grasp, about mysteries we're only beginning to glimpse, it might feel overwhelming. But perhaps that is part of the gift Webb has given us. To feel small and yet part of something vast. To feel humbled and yet uplifted. To see beauty not just in what we understand but in what we don't. The stars above are not only distant objects. They are reminders that we exist in a universe far older and larger than ourselves. Each point of light carries a story, and now, with Webb, those stories are being told with new clarity. The galaxies revealed by its mirrors are not just scientific data. They are invitations to wonder, to reflect, to ask questions that may never have final answers. And so here we are, beneath the infinite, listening to the whispers of ancient light. The telescope has given us images. Yes, but it has also given us something deeper. Perspective. Perspective on time, on space, on ourselves. It has shown us that the cosmos is stranger than we thought, and that our place within it is both fragile and extraordinary. As the journey of light continues, so does our journey of understanding. There will be more discoveries, more puzzles, more debates. Webb will not answer every question, but it will keep asking them on our behalf, and we, in turn, will keep looking, keep listening, keep wondering. For now, it is enough to rest with the thought that we are part of this story, that our curiosity is itself a thread in the cosmic web, that our questions are echoes in the great silence. The stars do not need us, but somehow, here we are, looking back at them, finding meaning in their light, and as you settle into this reflection, beneath the infinite, perhaps let the immensity of it soothe you rather than unsettle you. The universe is vast, yes, but it is also generous, sharing its light across billions of years so that we might see it, so that we might wonder, so that we might dream. Thank you for joining me on this journey tonight, for drifting with me across the earliest galaxies, through threads of dark matter, into echoes that have travelled across billions of years. I hope this exploration has given you something gentle to think about, something wide enough to carry your imagination while still calm enough to let you rest. If you found this soothing, you might consider supporting the channel by liking, subscribing, or sharing it with someone who would enjoy falling asleep to science. It helps keep these quiet explorations going, and it means I can keep bringing you new stories from the universe. For now, let the stars stay with you, not as puzzles to solve, but as companions to dream alongside. The galaxy's web has shown us will still be there tomorrow, waiting for us, patient as always. Tonight they can simply be light in the distance, steady and timeless. I wish you a peaceful night, filled with calm thoughts and gentle dreams. Until next time, may the cosmos keep you company, and may you rest well beneath the infinite sky.